So let's start the conference part of this meeting that have two parts. Mini course that Rodrigo Freire and Professor John Baldwin delivered from Monday to yesterday. Very nice mini course. And today we start with the conference with my colleague, Professor Lucia Junqueira. We talk about elementary submodels in topology and set theory. Thank you, Lucia.
Yeah. Oh, thank you. Everyone can hear me, it's fine? Yeah. Okay, thank you. Thank you very much for the invitation. Thank you it's a pleasure to be here. Thank you for invitation. And I'm sorry I couldn't take part on things, but we're finishing my semester. We're 1 month late, so let's be a bit rushed, but luckily I could come to present. So, well, I hope I don't disappoint the audience because it'll be want to be too much. Okay? Won't be too much model theory or anything like that. It will be more topology and set theory, but anyway, that's my area. So the goal is to show a little bit how we use elementary submodels to prove things in set theory, and I'll get some chalk here because I'm going to need in set theory and topology. So not much new things, more old stuff, but anyway. So let's start. So like the use of elementary submodels as a tool in set theory and general topology, I think we first see in the literature around the 80s, but the first paper that really was about it, like really concentrated this topic, was this paper of Alan Dow. It's a paper that was published in 1988 in the Topology Proceedings. And in the paper, he reproves some results and he does something new. So like was the first one that really talked about applications of elementary submodels in topology. And then after that, I think it was the paper that kind of caught attention to it. And then after that, several other papers starting appearing, like surveys and people doing things more carefully, because in Alan's paper, things are not done very, very carefully. It's not an easy paper to do the details. Many others, so I just mentioned here, there's this paper of Sokup. It's a paper in archive, I don't know if he ever published it, where his specifics about applications of elementary submodels in infinite combinatorics. And I think he put an archive around 2010. And has some, for instance, some results in graphs and other things. So it's really more combinatorics and set theory there. So we don't use much things from elementary submodels. So that's why I said, like, I hope people are not disappointed. We use just very basic things. I didn't write the definition of elementary submodel. I imagine everyone knows. We use a lot Tarski criteria. So just to recall it. That's what we use it quite a bit, but use a bit of elementarity too. And Loven's-High-Scollin is what is going to give us the models that we need. Sometimes we just, and the language we always set theory language with. So that's the usual. And many times we just want countable elementary submodels, then we get straight from Loven-High-Scollin. But sometimes we want elementary submodels with more properties. And then we need sometimes do a chain of elementary submodels. So depending on the application, you do different constructions. And but nothing very complicated either, right? Like just basic things. And it's always, well, we want to take elementary submodels of the universe, which of course we can't. So we look the way to go around. We use the sets, the H theta. I hope everyone heard of it, which is a model of ZFC minus the power set axiom. Then you can always get theta enough, so you can have enough power set axioms to do all the proof you want. So many times we don't even bother, right? As you look at the papers, people don't even bother write the H theta, just think about V, and don't bother also to calculate which theta do you need. Usually leading with topology, you have the size of the topology, the power set, because you have the open sets, covering of open sets, and maybe 2 power sets is enough. Don't need a lot more than that. Okay, so what I plan to do today, and it has been used for both. It's used for old results, so as I mentioned, Alan Dahl in that reproved some results on that paper, but there are new things also that was proved using elementary submodels. And it has been used to do proofs, but also to construct examples, like both things has been used. And it's kind of interesting, like when you look, because like that started late 80s, early 90s when I did my PhD, but I could see that you have the people that use elementary submodel to do things, and they have people that try to redo the proof without elementary submodels. So you have the kind, for instance, in the 90s, Zoltan Balaguer construct a very important example of a Dawker space. Doesn't matter what it is, but he solved the important problem. And then he did the construction of use elementary submodels. And then I saw a presentation of that in Toronto of, I don't remember now, it was who did it, but redid the example, but now without elementary submodels. Alan Dahl has a proof that he did, and people were trying to take elementary submodels, and then there is one specific result that no one could take it out, so there's a bit of this maybe generation or being used to the old way or new way. And one type of proof that can be done very well with elementary submodels is when you use closing off arguments, and we're going to do one of them today. Because closing argument, you have to do this induction, then you have to figure out what you want to put in your transfinite induction. And the law of Heiss-Cullen does that work for you without you having to worry about all the specific formulas, what you need. It's just, you put everything there, throw everything under the carpet, and then you have what you need. So that's the complaint of some people, that elementary submodel proof, sometimes you don't really see so well, understand the construction, what's going on. So that's what I'll do. I'll do 2 basic, by now very standard proofs of using elementary submodels. They are classical results, one in set theory, one in topology. And then I'll talk a little bit about the work that I did on my research and have been doing that has to do at the topological properties by preservation of topological properties by elementary submodels. So kind of seen as an operation, but I'll talk about that later. Okay, so that was introduction. So the first 2 proofs, I don't know if everyone saw them, but they are kind of what people do nowadays to give examples. It's in Kuning. The older version of Kuning doesn't have elementary submodels. Now the new edition he included. So the first proof is just proving delta system lemma, which is a very important combinatoric result that you use in forcing and many things. So just recall, a delta system is a family of sets with a root R, that when you have every 2 different ones, the intersection is R. So any 2 sets that you get, they have this common intersection R. So this will be one, this will be the other one. That's A, that's B. And so that's the delta system. I don't know if everyone saw it before. And delta system lemma is much more general than that. I'm going just to show the simpler version, which says that every uncountable family of finite sets contain an uncountable delta system. So even with elementary submodels, you can do a bit more general, but I'll just do the first one to show a little bit the way you use it. So how do you show it? So, well, pick your uncountable family. So there'll be a few things I'm going to use about elementarity, but I'll mention it. I didn't want to put a whole bunch of results in the beginning. So I fix my uncountable family. I can suppose these uncountable families of it's finite subsets of omega 1. Omega 1 is on my elementary submodel because I'm picking H theta, pick theta enough, big enough to have omega 1 defined there. So I pick M. In this case, I'm just going to use countable. Pick M, a countable elementary submodel of H theta that contains the A in it. That's all I need in this case. So then the idea of the proof, after I typed, I realized maybe I could just do a draw, but so the idea of the proof is that I have my elementary submodel M, which is countable, and my family is uncountable, right? So my family A is uncountable, M is countable. So I have someone that's not on my model. So I have a set A here. That's not my model. It could be everything outside. Doesn't really matter to me if it's everything outside or not. So this, what I'm going to get is this intersection. This is my R, the intersection of A, M, and A. So define R, this intersection. So what you're going to look is the set of every delta system, every, should be a subset instead of belong, but every subset of A that has a delta system with root, I call D here. Oh, sorry, yeah, some typos. So every subset of A that has this root R, here should be an R. So all the family F of subsets of A that's a delta system with this root here. That's my F. Well, so notice that the parameter, so R is a finite subset of M. This is my R. But every subset, finite subset of M, since it's finite, I can define it in M. So then, and R finite, these two things implies that R belongs to M. So R belongs to M, my family A belongs to M, so this family F only have parameters in M, right? By axiom of choice, I can pick such a maximal family. So axiom of choice gives me there is an F that's maximal with related to inclusion. So using TARS criteria, I can get such an F in A. So I can get an F AA that's maximal with respect to inclusion, right? That's in the family. And I just have to show that this family, this maximal one, is uncountable. And the idea that, so I have to show that B is uncountable. The idea is that it's uncountable. So I have this family B here, which is my maximal family. So if I have B contained in M, countable, what happens? My omega also belongs to M, because I picked M. Well, I can define omega in M. Do a bijection between these and these, use there is a bijection in M, some elementary argument is going to give you that B is a subset of M. So if you suppose that B is countable, if you have that B is countable, you're going to have that B is a subset of M. So all the elements of B will be inside here, right? It's a whole bunch of finite sets that has these in common. But then I could add A to this family. A is not here, so when I add to the family, it's an extension of B, and since my root R is A inter M, when I add A to my family, it's going to be an element of my set F there, right? Because this one and this one has intersection here, but with everything else is outside, so the intersection will be exactly R. So I get a contradiction because of maximality. So in this case, I use the model like to separate this part that's inside and contains everything inside, and I have this part outside that I know it's new. So sometimes it helps me to know there are things outside, and effects outside, I can prove relations and things about it. So that's the way the proofs go. So then you get a contradiction. So B is uncountable. B is the family that you're looking for. So that's a way to prove. Theirs can be more general, but a simple way to prove the delta system lemma using the elementary models. Okay, so that's the set theory application. That was, I think, was done first by Alan Dow in his paper. but it's 3 lines, and I remember people couldn't understand it very well, what was doing, and then it was better written afterwards in other places. But anyway, it's a simple proof. Now I'll do application in set-theory topology. So there is some, like when you look at what we call cardinal functions, you're trying to determine many times the maximum size of topological space. And so there are lots of arguments that we use what we call post-Shapirovsky technique. So you do this closing off arguments to construct to do some transfinite induction to show the maximal size of a topological space is continuous or 2 to the kappa or something. This kind of construction you can very easily translate to elementary models. So that's the example I'll do now. I'll need the definition of a Lindelof space, which is an important generalization of compact spaces. A space is Lindelof if every open cover has countable subcover. And but can be done for compact. There's no problem. So people never heard of it can think about compact space. And was a question that was done. There's a question like in the 20s of last century, 100 years ago. So it was proved. People knew that metric spaces with countable base was had size at most continuum. And the question was if every compact first countable space had size almost continuum. That was the question that people tried to solve for more than 60 years. And Arhangelski solved it on I think the paper was published in 61. So Arhangelski theorem is a very important theorem in the set-theory topology, as then after people are still trying to generalize. There are other problems related to it that's still open. So Arhangelski theorem says that every first countable Hausdorff Lindelof space has size at most continuum. So in particular, compact first countable T2 spaces has size at most continuum. It's still open if you can get rid of T2 or Hausdorff. Like there's an open question if you can just do with T1. Very little is known about that. And there is a problem also if you ask instead of first countable, you ask every point is a G delta, which is countable pseudo character. There are some consistent results, but for a long time it's a very hard problem. But there are still open questions about it. So, and there are several other generalizations. I'm putting everything countable, Aleph 0, but could be done for any kappa. Just doesn't matter. Okay. Okay, so we're going to use elementary sum models to get rid of, not have to do all this closing off argument where I have to add lots of hypotheses to my construction. The law of high school will take care of that for me. So I start with my topological space, X tau. And in this case, well, first countable T2, Lindelof for all the hypotheses I need. In this case, I'm going to need a specific kind of elementary sum model. I want an elementary sum model that has size continuum, but I want to be what we call countably closed. Every countable subset of M, is also an element of M. So we call it, we say that M is countably closed. So it's closed for countable sets. And that's what I'm going to use. So if you want to close it for countable sets, then you need at least size continuum. So then I cannot have here. So it's closed for countable sets, so can have size continuum. And X tau in it, the elements I need, my parameters. And then since the elementary sum model has size continuum, it's enough if I show that X is a subset of M. If I show that, I'm done, right? Okay, so that's my goal. To get these kind of models, you do use elementary chains. You do an elementary chain of size omega 1 where you close off all the time for all the countable sets that you have previously, and then you can construct. So it's not very complicated to obtain this. So the proof is actually divided in 2 steps. So I have my space, X, and then I have M here, my space X. the first part is to show that this part here, when I look at X inter M, show that this part's closed. How do I show that's closed? And that's where I use the Hausdorff, the hypothesis of being Hausdorff. So to show it's closed, you have to pick a point and the first countable too. I pick a point here in the closure of the space, my point X there. The fact that's first countable, if this point is in the closure of X inter M, I have a sequence converging to it, right? So I have this sequence XM that's converge to my point. Well, this here I need the count to be closed. This sequence Xn is formed with elements of M. So I have this sequence here. It's a countable set, index and everything, but it's countable. So it's a subset of M because of my hypothesis on the model. I'm going to have that actually the sequence belongs to M. So I have this sequence here belongs to M. Well, but this sequence converges, so I know that there is a limit for the sequence, right? And now I can reflect this, use elementarity. The fact there is a sequence, the sequence belongs to M, all the parameters in M. By elementarity, there is one guy in M that witnesses that the sequence converges. Well, there is this Y in M. Here the T2, that's the only place I need it in the proof. So it looks like it should be easy to get rid of it, but it's not. So it's Hausdorff, so you have just one limit. So just one limit, X has to be equal Y, then X is actually in the model. So I show that every point that is in the closure is actually in the model. So then in the X inter M. So I show that's closed. Okay. I can use less than first countable to do this proof, like we have this proof called sequential, but I can't get rid of the Hausdorff hypothesis here. So, okay, why do I want it to be closed? So the fact that this is closed, this space here is closed, gives me that this space is Lindelof. The same thing for compact. Closed subspaces of compact spaces compact, closed subspace of Lindelof spaces. Lindelof, exactly the same proof that you pick the complement to complete your open cover. So now we just have to show that X is a subset of M. And it's by contradiction. You suppose there is one guy here that's not. Then I can, so what happened? If I pick a point here, this point here has a base, right? Because it's first countable. So every X has this base at the point and has a countable base. But X is in M. So I can say there is a countable base that belongs to M, right? Also by elementarity. So here I use elementarity several times. So every point has a countable base, but X is in M. They have the existential. There is one base that belongs to M. It's countable. So the fact that's countable, I have Bx subset of M. Why do I want that? Because then since these points is outside X inter M, I'm always going to manage to get one open set here that contains this point that doesn't have Y. Not set here, I just need T1. So I have an open set that is in M that has X, it doesn't have Y. So I can do that for every point. So I cover my X inter M with open sets that belongs to M, but doesn't have Y in it, right? It's Lindelof, X inter M is closed. It's Lindelof, since it's Lindelof, has a countable subcover. So I have this countable subcover I called here, I call D here. So it has this countable subcover. But this countable subcover, again, by my hypothesis, that has our countable subsets belongs to the model, this countable subcover actually belongs to M. So M, what does M sees? M sees that the union of D covers the whole X. Like if you reflect that formula, then we just say that, put all the intersection, everything. So the family D covers all X, but this reflects outside. So then X has to be union of D, contradiction because Y was not, I thought I had to put the union here. Y doesn't belong to union of D, and you get the contradiction. So this shows that actually X has a subset. The original proof for Rangelsky is not that one that people see nowadays. The one that you see in books are the one using Paul-Shapirovsky technique, that you do a transfinite induction, or you keep putting points, and you do a list of things you need in your transfinite induction, pick the union of everything, and you show at the end this union equal your space. So it really has the same kind of flavor now when you look at the original proof, but then you don't have to do this construction. The override scholar will take care of it. But the other parts, like you have to show that this union that you obtain is closed, and the other parts are very similar. So that's the proof. Okay. So that's what, like two very basic, there are lots of other proofs in the literature that can be found. I decided to give these two because I think they are most well known. So then what I did, like when I was studying there in the 90s, like these elementary models, they are being more and more used. And then there are things that you're using here, like when you look at this X inter M, we show that it's contained in X and is a subspace of X, but it's a closed subspace. So what the Frank Toll, my supervisor, and I started to do is to study the tool itself. We would see, so what general topology, what we do, like many times, you have the operation. So you take products, you take subspaces, you take quotients, and we're always interested in preservation of topological properties. So we define the topology course, you define product of topological spaces, then you're going to show, oh, product of T2 space is T2, product of compact space is compact. Normally it's not true. So you're always investigating what preserves under the topological operation. Continuous function, what preserves which topological property. So it's a general theme in topology to study which topological properties are preserved when you take some specific operation. So we decided to do that with this kind of operation of taking elementary submodel. So what we do, you pick topological space. Still didn't get used to the button. You get the topological space, pick elementary submodel that always contain it, so you can do any reflection argument, what you want. So I'm looking at Xm as being the intersection, X intersection, but I'm not looking at it as necessarily as a subspace, because I'm just going to consider the open sets that are in M. So eventually it's a weaker topology than the subspace topology. The subspace topology, you would just do this, pick out the open sets in tau and intersect with M. Now I'm adding this restriction to the subspace topology. My open set has to be in M. So we're defining a topology that eventually is weaker than the subspace topology, right? Well, for the rest of the talk, always M will be elementary submodel that contains the topological space, the pair, the set and the topology, so I don't have to repeat it. And then you can ask several questions. You can ask when it's a subspace, when it's a closed subspace. That's something that Frank Toll started, and I worked with him for a while. Which conditions on XM ensure that you have the quality? So like you can really crush down the property. And which topological properties are preserved. I'm going to focus more in this last one. So for instance, when you look at preservation of topological properties, we can look both ways. You can look downwards and upwards. So I just give two examples of results. This, as usual, like in separation axioms, everything works well with Tikhonov space, but not to normality. Here it's not different. So you call downward preservation. So downward preservation, if X has the property, then XM has the property. So let's try to give an example instead of giving a definition. So if X is Ty, X T2, T0, T3, whatever you guys want, then Xm will also be. But also you can look the other way around. Look, if a property from Xm goes up to a property of X, so then we call it upwards preservation. So this I showed in a paper of mine. If Xm is compact, then X is compact. So X compactness goes up, right? I should say that, before I pass to the other slide, like we start looking at this when I was doing my doctorate in Toronto. And at the time, what I was looking first was preservation of topological properties by forcing. So what you have when you do forcing? So, so you have your ground model V, and then you have your topological space here, right? When I go to the generic extension here, if it's non-trivial, I'm adding new unions. So since I have more unions here, the topology here is not closed by unions anymore, usually, right? So eventually this is not a topology in my generic extension, but it's a base for topology. The only thing you'll be missing is just the union. So I can look at the same space X, but with a topology, let's call it tau G, in this generic extension. So it's the same set, but I'm looking at now, I'm picking this topology ahead, and I'm adding all these unions to have my topology. This study looking what happened is, that started in the 80s, also started in the 80s. I think a big part of motivation for this is arguments that were done when you use super compact cardinals. Frank Dahl and Baldwin were working on this. Because when you do super compact cardinals, they had some arguments they were doing. I know they're doing super compact, but other large cardinals. You look at generic extensions, and since you have the elementary embedding, you, for instance, add J of kappa coin reals. Then they had arguments, they will break your forcing here in two parts. And then you have this intermediate, but then they were looking what's happening with the topology in these parts, and you wanted some preservation of the topological property. So in particular, the normal Moore space conjecture was something that there is this paper of Alan Dahl and Bill Weiss and Frank Dahl, they were doing this kind of argument. So they needed the preservation of the topological property to carry on these arguments. So because of that, sorry, there was some arguments that were appearing, some proofs where they talk about preservation of topological properties. And then in the open problems in topology, the first book on open problems in topology, there is a paper of Steve Watson called Problems I Wish I Could Solve. And they had a specific section on the preservation of topological properties by forcing. And that's what we started working on. We started looking at preservation by forcing. And then Stevo Todorcevic at the time said, well, if you're looking at preservation by forcing, you should look at preservation by elementary submodels. And that's how we started looking at this. And the similarity of both, so there are of course, a big difference between them. The kind of results, the kind of techniques you use, right? So, but the similarity is that, you have in both cases, so when I pick the elementary submodel, when I look the space here, I have X tau, but I look this inside M, what I'm doing, I'm picking X inter M, I'm picking tau inter M, right? When I look this outside to take my space that I define, what I'm doing is just adding the unions. So in some sense, I'm doing the same thing I'm doing when I go from V to VG. What I have to do is look inside M, then I have inter X inter M, tau inter M, and all the unions that are just in M, because I'm living inside M. So if you live inside M, that's what I have in unions in M. When I pick this, but I'm not living inside M anymore, I'm going to have all these new unions. And so in this sense, when I go here, is the same thing I'm doing here, because I'm adding all these unions. The techniques are very different because one is elementary, the other one is forcing. So I look at completely different things. I never saw anything, like more logical or comparison of both things looking this way. Okay, what could you say in terms of studying formulas and everything that could actually prove the similarities? Like maybe there are things between the forcing and the elementary model that you could have in common, that you could unify some of the results. But I never saw anyone studying that. But there is some similarity, but the techniques will be very different because, well, forcing, you do different forcings, there are different types of elementary models. But there are some comparisons that were made. For instance, compact is an interesting property to look at. Okay, our time. Compact has an interesting property to look at. There is a result that's already known that knows that scattered spaces are spaces where every subspace has isolated point. So you can do the burst and Cantor decomposition in levels and actually go all the way. Because the isolated points or the accumulation points, you have two ways of doing it. Not really important, but it's a very specific class of topological spaces. And it was already known that this, in the class of scattered spaces, compactness was always preserved by forcing. It's easy to see that compactness is not preserved by forcing because you can add coin reals to the interval 0, 1, and then you lose compactness very easy. And the same for elementary models, by the way. And so then we knew the results for forcing, then Tol and I showed, that's a paper appeared in Fundamenta Mathematica in 2000 something, I have the reference later. We showed that for elementary model is also preserved. So X compact scattered is preserved for any elementary model. So that's one result that you have the same happening. For forcing and for elementary model. Compacted 2 is preserved for any forcing, for any elementary models. It's not preserved in general. Kuning was, after the work I did with Frank Tol, Kuning worked a bit about this reflecting compactness, reflecting downwards, and upwards always possible. And then he defined this term, a compact space is squashable. Because of course you can reflect if you have xm equal x, like it's a trivial way to reflect. But suppose you have, say the elementary mod is squashable, if you can reflect compacts in a non-trivial way. So there's a paper of Kuning, Todd Eisworth did some work on it. This is squashable and actually involves large cardinals to be able to get, to squash the compactness non-trivial, which is like Chang's conjecture. There are some models. You need these weird models to be able to do this reflection. So he shows, for instance, that 2 to the lambda is squashable if you have, I think it was extendable cardinal, but you need a large cardinal for that to happen. So that's some work that's done that involve large cardinals. More recently, with some students, we're looking, well, another theme that's very common in topology is, I do something for compactness. What happens if I generalize compactness? What happens if instead of compacts, I put Lindelof? So lots of the work, lots of important problems came from that theme. So I have something happening for compactness, what happened for Lindelof? Can I generalize the results? Which hypothesis I have to look? So that's the work I did first. These are two former students of mine, Robson and Rodrigo. So first with Robson, then with Rodrigo, we worked on this study of generalizing things from Lindelof to compactness to Lindelof. We look at first with Lindelof, with Rodrigo, then we look at other strengthening of Lindelof, which Menger, Rothberger, there are properties that have different kind of flavor. They are related to selective principles and topological games and this kind of thing. So anyway, I'm not going to talk about them now. And we could get some results. They are in a paper that's not submitted yet, but we got some results. For instance, the result about, first the upward reflection. So the upward reflection, xm to x, you cannot expect to happen for Lindelof space in general, because I could get M countable. So if M is countable, XM will have, remember that my XM has a base, the tau inter M, right? That's the base for my topology. So if my M is countable, this space will always be second countable, right? So for M countable, XM is always second countable, so always be Lindelof. So there is nothing to do. So I can't expect to reflect in general. So I need some property. It's natural to ask for countably closed. That would be the first guess, countably closed, because then you put all the countable sets. But you can actually get away with something weaker. It's a property that was defined by Alan Dole in that paper from '88, I believe, called omega covering. So I don't need the closing of the countable subsets. I just need some subsets. So space M is omega covering if every countable set A is contained in one that belongs to M. So that's much weaker than countably closed. And the advantage of omega covering is that I can get omega covering sets of size omega 1 models. So it's possible to get omega covering elementary models of size omega 1. It's actually under CH, then M omega covering is equivalent to M countably closed. And this is equivalent to CH that I showed in my paper of. So it gives for CH is equivalent that these properties are equivalent. And to construct this also, again, you do elementary chain and keep going of size omega 1, so it's not too complicated to construct. And this property is enough to get Lindelof going upwards. This property implies omega 1 subset of M, but omega 1 subset of M is not enough to go upwards. But with omega covering, I can. So then Lindelof is reflected upwards. That's a bit older. And but in the joint work we did, we showed the equivalence. That equivalence for scattered space is also done for Lindelof spaces. So it's equivalent for scattered. Here I need regular. So for compact, I just need T2 because compact T2 implies regular. But in the proof, actually, what you use is regularity. So I had to increase a little bit. We had to increase a little bit the separation axiom, because in the argument I need to pick open sets and the closure inside of other open sets. So I really need the regularity, which I got for free for compacts, but I don't get for Lindelof. Lindelof T2 spaces don't have to be regular. So we had to change this. But then if I put regularity, which is not too bad to add, then I have the equivalence. And I actually thought when we were thinking about this and trying to prove, I thought I would have to add condition on the elementary submodel too. The same way before. Here we got the result, but we had to ask for elementary submodels omega covering. I thought maybe we would have the same thing. I would have to assume omega covering, countable closed. So it's actually, I don't need anything. Yeah, if I assume a regularity, XM Lindelof is equivalent to X Lindelof for any elementary submodel. So I really have the same result we had for compactness, the same preservation in the class of scattered spaces. Maybe I should say that in the character of spaces, Menger, Rosberger are all equivalents. So the equivalence actually is bigger, have bigger equivalence. And then you have equivalence by preservation by forcing too and everything. So anyway. Okay, to finish, okay. I just like to finish, like going back to this idea of comparing preservation by topological, by elementary submodel and preservation by forcing. There is this definition of Frank Toll that's also related to Rothberg and Menger. Well, actually not a very good term, but that's the term he gave. He called the Lindelof space indestructibly Lindelof if it remains Lindelof after any countable closed forcing. So Lindelof can be, for instance, just to have an idea, adding Cohen reals preserve the property of being Lindelof. Adding random reals preserves the property of being Lindelof. For Cohen reals, there is another proof of Landau. For Cohen random reals together, there is a combinatorial thing called endowment that can prove for both together. This comes from a proof I did in my thesis. So Lindelof is preserved in certain forces, but it's not preserved for other. If you add, you look at 2 to omega 1 and add a countable Cohen real with countable conditions, not a Cohen real, but Fn omega 1 to omega 1. If you add that to this, then you destroy Lindelof. So you can destroy Lindelof with forcing. That's not, there are some examples that you can find. So it's not preserved in general. That's why here he added this countable closed forcing. So the question is, Lindelof space can be destroyed or not by countable closed forcing. And the motivation here, again, is argument related to large cardinals. And it has to do with the problem related to Archangelski problem. So going back to Archangelski theorem, remember that I mentioned there is an open question about, still some things open about weakening the first countable going points G delta. So with Baumgartner, Frank Tall and Baumgartner were working this problem. They wanted to do a large cardinal reflection argument. And for the argument to work, they need the preservation of Lindelof by countable closed forcing. That's where the definition came from. So it came from this, the need of doing a large cardinal argument. So he gave this definition. So look, so here, like you're asking for preservation of Lindelof by some countably closed forcing. So what we're trying to do is see if you could relate that to the preservation of elementary submodel somehow. So you can ask, is there a destructible Lindelof space such that Xm is not Lindelof for some countable closed elementary submodel, or the other way around? We actually don't have examples for any of them. So like, can you kind of somehow, going back to this idea, to get some comparison between them, can you say something about it? Actually, this problem of destructibility is still open. We still don't know. There is no example of that. There is no example of, and there is some work that was done by Frank Tall and Skipper that related to games, topological games, and some partial results. But first, we don't have an example of Lindelof space that is structurally Lindelof, so we don't know. There is very little done about that. Well, like concrete results, a lot of parts of results, but so it's still open, the problem of getting a Lindelof not structurally Lindelof space. So so that could help with it, but we were trying to combine instructable Lindelof with Lindelof not being preserved, or maybe being preserved, anyway, by countable closed forcing. Do you want to compare these two and see if they're actually different or not? And we don't have anything. What we did, we look at that Frank Tall and that paper with Baumgartner. They had several conditions, so there is some list of conditions of Lindelof space to be indestructible Lindelof. Which conditions I can put in a space to know for sure that the Lindelof is preserved by countable closed forcing. And actually, they show, this can find in the handbook, it's enough to look, I don't have to look at any countably closed forcing. If I can be preserved by this one, that's enough. So that's the only force you have to look at. If you show that Lindelof is preserved by this forcing, you can prove that's preserved by any countably closed forcing. So it's the same thing to ask if it's preserved by this. So here are some conditions. So it has like the paper, I'll put the reference there, there's this paper where they have this list of spaces that are Lindelof, but the preservation Lindelof is preserved by countably closed forcing. The knowledge is confusing, so I get confused with it. But then we look at this list, and then most of them, we could show that the same happens for for preservation by elementary submodels. So X is hereditary Lindelof, countable closed, and most ones. So it's the same list that he had there, we had here for elementary submodels. So it didn't help us to differentiate these two things. Preservation by elementary submodels, preservation by countable closed forcing. So I think that's what I wanted to talk about. So some reference, that's the first paper of Allen Dahl. That's a paper of Sokup I mentioned, that's on archive. That has has new proofs. So actually it's a paper where Large Sokup, he redo some proofs, infinite combinatorics. There are some things related to graph, but also he has new results. That's the first paper Frank and I did related to this study of preservation of topological properties by forcing. That's when we start looking at the compact preservation, and that's the one we're doing now. And that's the paper where Frank Toll has this paper, but also has another with Baumgartner in the topic of destructible Lindelof spaces. But that's where he introduces the definition. And I think that's all. Thank you.
Thank you, Lucia. Questions? Comments?
It's just a simple question out of curiosity, and because I'm not so much familiar with the applications of forcing to topology. But when you talk about these countable forcings, you're only talking about Cohen style forcing, or do you apply other kinds of forcings?
No, it's always Cohen style.
Yeah. So this is a standard in
Standard
topological
forcing.
applications.
Yeah.
It's always the Cohen.
I don't think I ever saw an application with other kind of forcing.
All right.
Could be because the topologists just know this type of forcing. I don't know. But I never saw. Yeah.
Because you talk about it, but you never say it. So so maybe this is the standard way.
Yeah, it's always Cohen forcing. Yeah.
Thank you. It's just.
Or questions, comments? Or if not, thank you, Lucia. Okay, so let's start our conference. Let's continue our conference with Professor Rodrigo Bacelar of IME-USP. Thank you, Rodrigo.
Well, can you hear me fine like this? Like this? Not used to talk. I'm talking on that. Okay, well, yeah, one of the malicious rumors that I know circulate about me is that I'm some kind of vampire, because I'm never seen anywhere before 2 p.m. So, well, I'm here 11 a.m. Safe and sound. So I'm grateful to the organizers of the conference for giving me the opportunity to refute this one malicious rumor. Others remain, of course, but these are either harder to refute or perhaps true. Okay, well, this is not so much about definitions and the foundations of mathematics, which is the theme of the conference, but it's in good parts about definitions, which is, I suppose, close enough. Okay. Well, we can say, at least in some sense, that logic, like any science, has its concepts and its laws. Listen, in some sense, we can say this. Now, the concepts, the logical concepts, tend to be naturally regarded as certain functions. So we will speak more concretely of logical functions. And the laws tend to be naturally regarded as certain rules. So we speak more concretely of logical rules. Okay, so I'm thinking here of the logical concepts that appear, roughly speaking, inside logical systems of familiar kind, such as classical propositional logic, or classical predicate logic, or some modal logic, etc., etc. So in classical propositional logic, we would have such things as negation, conjunction, disjunction, implication, equivalence, exclusive or, force, verb, etc. So what are known as Boolean functions or true functions. Operations of finite arity over 0, 1 or TF. Okay. These would be the logical functions in the context of classical propositional logic. Then, say in mode of propositional logic, we have, besides these things or replicas thereof as well, other specifically modal concepts like necessity, possibility, etc. Necessity, possibility, contingency is an interesting one. Possibly true and possibly false. Strict implication, necessity of the material implication, strict equivalence, etc., etc. So we have a bunch of modal functions. Of course, what these are will, well, the appropriate notion of modal functions will depend on what modal system we're talking about. I tend to concentrate on the standard system known as S5. But anyway, other systems will have their modal functions. And well, in predicate logic, we have things like universal quantification, extension quantification, identity, which maybe we want to consider as a constant function. So that's also a function, right? So in the case of predicate logic, there are some various questions that arise, but in any case, something like some logical functions will appear there too. And so that's the kind of thing I have in mind when I say logical functions. So there are logical concepts that appear in various logical systems, roughly speaking. And well, logical rules are things like say, if you're in classical logic, you might have rules of conjunction, introduction. Right, so this P, Q, P and Q. Right, so in general, I mean, the sense of rule that I'm going to use here is the rudimentary sense of an ordered pair of a set of formulas and a formula. So it's a kind of Hilbertian scheme, right? So a rule is an ordered pair, set of formulas, which I usually write like this or like this. Right. So that's the usual rule of conjunction introduction, and that's conjunction elimination, right? From P and Q to P, from P and Q to Q, disjunction introduction, from P to P or Q, from Q to P or Q, and there's other familiar rules: double negation elimination, double negation introduction, and so on. Now, an important special case is zero premise rule. So gamma can be empty, of course. So an important special case is rules with an empty premise set, or axioms, as we might call them. So an example in classical logic is exclude middle, right, in the empty set, P or not P. Right. Another important rule is what's known as disjunctive syllogism from not P or Q to Q. Right. Some of these will play some role later on. But anyway, this is the kind of thing I mean logical rules. And okay, but these are some classical ones, but anywhere else there'll be such things, modal logic. Maybe I have from necessary P to P, from P to possibly P, and so on. Okay. Now, coming to definitions. Obviously, an important thing about logical functions is that they generate other logical functions. Right? So, we have negation and disjunction, and in some sense define implication. Indeed, from negation and conjunction, negation and disjunction, we can define all true functions, as we know. So anyway, an important thing about logical functions is that they have this power to generate other logical functions by definition. That's definition is we might say the natural mode of reproduction for this kind of animals, logical functions. Functions generate other logical functions by definition. That's the natural mode of reproduction. So generation logical functions by definition. Okay, these are relatively basic objects here, because they are not metaphysically basic. There are things inside functions and modes, but they're more comparatively basic, let's say, in this context. So definition is something like this. I want to give the various things. Most things I'm not going to precisely define here in particular definition. Partly for reasons of time, but also partly because these things these ideas are supposed to apply in different contexts, and the precise definition will be somewhat different. Often be somewhat different in different contexts, so that it wouldn't even be possible to give precise definition. So I'll give some examples to give the idea of the kind of thing I mean. So this is something like this is a definition. Right? So we put together the given logical functions to form a compound which expresses the desired function or the defined function. Right? Or if we have just so this shows that negation, disjunction defines material implication, because we have this. Also, let's say implication alone defines disjunction. We have this nice definition of disjunction from implication alone. Right. Or I don't know. I suppose this is clear enough already, but let's say to give another draw example of definition. We have conjunction and equivalence. This defines disjunction because we have this draw definition. P or Q is the equivalence of equivalence with conjunction. Right? Okay. That's a draw definition. Yeah, or if we are in modal logic, say, be able to say something like this defines possibility, right? Because possibly P, not necessarily not P, and so on. Okay. Okay. So that's the kind of thing I mean by definition. That's the natural mode of reproduction for logical functions. Now, the natural mode of reproduction for logical rules is what we call derivation. Derivation. I want to speak of derived rules, or derivable rules. Now, what does that mean? Well, it's a rather similar to the definition, which is put together the given rules in such a way as to produce the desired derived rule. So derivation is a derivation of a rule gamma alpha from a set of rules H is the same as a deduction in natural sense, a deduction of alpha from gamma via the set of rules H. So, for example, if you have a rule of double negation introduction, this set of rules, unit sets, derives a rule of quadruple negation introduction. Because, well, so introduction is from P to not P. Right? And well, we can derive this because we have to reduce not P from P via this rule alone. Okay, so start P by this rule, not P by this rule again, not P, which is what we want. So there's a derivation of quadruple negation introduction from double negation introduction. Or I don't know, we suppose we have a conjunction elimination. And conjunction introduction, the two rules of conjunction elimination, the left and the right, and conjunction introduction. This derives a rule of might call conjunction commutation or something. That is to say, this, right? Okay, because we can go P and Q by conjunction elimination, P, Q, now by conjunction introduction, Q and P. Okay. Okay. Or another example, if we have conjunction elimination, both conjunction elimination rules, conjunction introduction, both, I suppose we just need one, but anyway, disjunction introduction, and disjunctive syllogism, this derives, well, this non-contradiction is more commonly called ex falso quadlibet or ex contradictione quadlibet. P and not P to Q. Because we can go P and not P, P not P by conjunction elimination, P or Q by disjunction introduction, then using not P and P or Q by disjunctive syllogism Q. Okay. Okay, so that's the derivation of rules. Next, there'll be the corresponding closed classes. So a set of rules might be such that every a set of functions might be such that every function definable from the sets in the set, in that sense, close under definability. So this we call maybe a system of functions, or maybe a clone, although clone is used in a more special sense. So let me explain this. The system is the general term I tend to use here. It's just a set of functions that's closed under definability in the sense that if a function is definable from the set and is in the set. But there's also the special case of such a system where we have these so-called projection functions, which have a somewhat trivial character. So projection function is something that selects one of the arguments, right? So, for example, the projection of the 4-array projection function that selects the second argument is a function satisfying this for all x, y, z, u in the universe in question. This will be y. E4 to apply. This is y. Selects the second argument out of these 4. And similarly for any n greater than or equal to 1, any I between 1 and n. Projection of the ith place of this n arguments. And a system containing, okay, here I'm talking about operations. These are logical functions, so-called, and not always exactly operations. So there's some complications about that, but essentially there will be some kind of projection functions, even if they are not operations, and so cannot be characterized in so straightforward a manner. Okay. So systems containing all such projection functions are what we call clones. Okay. And these have some special interest. Now, the set of rules close under derivation, in the sense that if a rule is derivable from the set, then it's in the set. We might call logical systems or simply logics. This coincides with, for people who are familiar with the abstract logic literature, this coincides with, in most usual cases anyway, will coincide with, for certain kinds of language, etc., it will coincide with the notion known as a structural consequence relation. Right? But here we characterize it in a different way. It's a derivation closed set of rules, but it's co-extension with the structural consequence relation. No. So, for example, we can consider the system of all true functions, right? All true functions, and then there'll be the various subsystems of that system. For example, the functions generated from these two. This is not all true functions. It's an interesting system. Post studied this class of systems, all subsystems of the system of all true functions, and made a complete determination of these systems. There are innumerably many such systems. This is known as post-lattice, the class of these systems. Well, later there was much study of the case of k-valued functions. So instead of just two valued functions over 0, 1, or tf, one considers k-valued functions over set of k elements, which usually fixes this set, finitary operations over this, and then there's a class of all systems of k-valued functions. This has been much studied. This is the main object study of so-called clone theory. Yeah, in this case, I mean, for k greater than 2, the size of the class is always size of the continuum, no longer merely the. So it's, I mean, as is suggested by this, is more complex, but so it's not known thoroughly. Let's put it like this, like post-lattice is. But it's an interesting thing. There's much is known about it. Yeah. So this is yeah, but I mean, and there are other cases, like we might consider all modal functions in the sense appropriate to some system like S5, for example. And there's the system of all S5 modal functions, and we may consider the class of all subsystems. Also an interesting object, or really any class of logical functions you take, you can consider this kind of issue. Yeah. So depending on what kind of logic you like, intuitionistic logic, relevance logic, or whatever, you can amuse yourself with this kind of thing. Okay, so this is this kind of investigation called clone theory. So this is the study of such clones or systems. That's the name of the subject, clone theory. Well, the theory of logics it doesn't have a very standard name, but perhaps we can call it abstract logic. It's the study of logical systems. Yeah, actually, the use of the term here is somewhat misleading because, I mean, the theory of logics has some more abstract and less abstract parts. I mean, we can have concepts and results that concern logics in general, in complete generality, just arbitrary logics. So develop theory for logical basis, for example, and various other things in connection with logics in general. We can also study logics in a certain special class, natural special class. And this is actually more what I'm thinking about here. So just as in the case of functions, we can take okay, let's take this natural system, all true functions, and we can study the subsystem. This is a natural thing to do. The same way we can take classical logic in some reasonable set of connectors, say negation, conjunction, disjunction. We take classical logic in that set of connectors. Is an important logic. We can study all the sublogics of that logic. It's a natural thing to do. Right? We might call them subclassical logics. All the sublogics of classical logic in this sense. All the closed sets of rules that are included in this logic. So this is a kind of, I mean, the more general study you might call maybe general abstract logic, which would be a subfield of the famous field general abstract nonsense. And this more special study, we might call special classes of logic. We might call maybe special abstract logic. I don't know. So here I'm thinking more of special abstract logic. So in the case of clone theory too, there is a distinction, more abstract studies and more concrete studies. Things like the study of post-lattice or the corresponding thing for k-valued functions are on the more concrete side. Right. Okay. Okay, I want just I want to add a little about the flavor of these theories, the things we actually do. I'll make some brief remarks about that will end the talk. Okay. Okay, we can distinguish what I'm going to call level 0 activities and level 1 activities, and that's all. There's only these two levels. So level 0 activities. The most rudimentary everyday things that we do in this kind of study is in the case of clone theory, we show some claims of definability and some claims of undefinability. We show also, oh, this function is definable from these functions. Or show this function is not definable from these functions. That's the most rudimentary everyday activity of the clone theorist. And similarly, in the case of abstract logic or the theory of logics, the most rudimentary thing we do is to prove derivability and underivability of rules from a set of rules. Okay. Well, how do we do that? Well, very different to cases, the positive and negative case. Well, if we want to show definability, practically always what we do is just define the thing. Like I've done here some examples. I want to show, okay, this is definable from this. Okay, well, then we define. It is usually easy to define something. Occasionally a little hard, very rarely hard, but it's practically always that's what we do. Give a definition to show that a function is definable from a set of functions. Okay, so in complicated cases, we might go through some intermediate functions. Right? So from these, we can define this, we can define this, we can define this. Now, using these, we can define this other thing. Yeah, that's it. But essentially, it's this. We give a definition. And similarly, to show that the rule is derivable from a set of rules, we give a derivation, like we did here in some examples. This is derivable from this set. Okay, normally the thing to do is to give a derivation. And again, it's usually easy, occasionally a little hard, very rarely hard. Okay. That's probably an exaggeration. Sometimes it's hard, but often it's easy. Okay. Okay. But what about undefinability and underivability? I mean, we need to do something clever. Okay. And so here comes, we need some tools to show this. And there are two tools in the two cases. So I put here before the level 1 series, so it'll come at the end. So the key tools of these two subjects. Normal forms and relations. In the case of clones, clone theory, and normal forms and matrices in the case of abstract logic. Right. And relations, okay, I'll talk about normal forms later, soon, but relations are what we use to show, typically use to show undefinability. And matrix is what we typically use to show underivability. Okay. So relations in the the most straightforward case, some cases this needs to be modified, but in the most straightforward case, they're just relations and extension in the usual sense. So if you have, say, we're talking about case of k-valued functions. It might be the special case of two-valued functions. And we have the functions, our logical functions, so-called, which are any finitary operations over this. And then I have relations over this in the usual sense, set of m tuples. And there's this important notion of a function preserving a relation. So this is n area, this is m area. This can be anything, there's no dependence between n and m. Preserves or is a polymorphism of relation R. This means for all A1, AN, let's write like this, B1, BN, etc. In this set there, if that's what we're talking about, it could be any set really. This means that if for any such things, if R holds between A1, B1, etc. Okay, here there are as many things as the arity of R. And holds between A2, B2, and so on, and R holds between AN, BN, and so on. Then R holds between B1, BN, and so on. Okay. Now we apply the function in the rows. And some special cases of this are very familiar. I mean, of course, the special case of one relation of arity 1 is very straightforward. We're just saying that if suppose R has arity 1. So we're just saying if A1 is in R, and A2 is in R, and A is in R, then FA1 AN is in R. So for example, in the case of 0, 1, we can have the notion of a T-preserving function, or 1 preserving. T, if we're talking about T and F. T-preserving function means if this is T, and this is T, and this is T, then F of this is T. In other words, F of T, everything T is T. So various functions are like that: conjunction, disjunction, implication, equivalence, not negation, of course. So this is a straightforward notion of preserving a property. Preservation of binary relation is also known in familiar from special cases like an order relation. So there's the usual notion of a monotone function. Right? This is an order relation. We're saying if A1 is less than or equal to B1, and so on, and AN is less than or equal to BN, then FA1 AN is less than or equal to FB1 BN. i.e., F is a monotone function in the usual sense. I mean, with respect to this order relation, the usual sense of the term monotone function. Or in also a congruence of an algebra is an equivalence relation which is preserved by every basic operation of the algebra in this exact sense. So there are some familiar special cases of this, but this is a fully general notion. And then we have these classes of the form polar, i.e. all functions which preserve R. Okay. Or more generally, we might have a class of relations K. Then we have the notion of set of functions which preserve every relation. Okay. And these are actually precisely the clones. Precisely the clones. The clones are precisely the classes of the form Paul K or some K. So here you already see this part of the reason for the importance of clones among systems. Yeah, the polymorphism classes. Okay, well, how does this help with undefinability? Well, if one wants to show that a set of functions does not define a function f. Well, I should say first, it's easy to see that if certain functions preserve a relation, then so does any function which is definable from these set of functions, from these functions. Right, so if every function here preserves R, right, so for R, then if a function is definable from C, then it must also preserve R. It's easy to see this from definitions. So, in order to show C does not define F, the usual thing to do is to give a relation such that every function in C preserves that relation, but F does not preserve that relation. So we saw here, well, I erased it in the case of conjunction and equivalence. This defines various things. Defines the junction, defines implications, easy to see. P plus Q is P is equivalent. P and Q is equivalent to P. Okay. Defines various things, but does not define, for example, negation. Okay. This does not define negation. How can we show this? Well, this property. These things are T-preserving. Okay. So, clearly, right? So everything that they define will have to be T-preserving too, but negation is not. So they don't define negation. Okay. Or if you take these functions, they don't define negation. Why? Well, they are all monotone. They all preserve the natural order of true values, 0 less than 1 or f less than t. So everything they define will also preserve that, but negation doesn't. So it doesn't define negation. So that's the way to show undefinability. To show underivability, the usual thing to do is use the concept of matrix. Now, this is perhaps more familiar. A matrix is just an algebra together with a subset of the universe, of the algebra. Matrix is a ordered pair AD, where this is any algebra, and this is a subset, any subset of the universe A, of the algebra A. Usually called the set of designated elements. If you think of the elements of the universe here as propositions, so the operations will be certain operations on propositions, and D would be normally thought as a set of true propositions. So there is a natural notion of a logic associated with a matrix, right? So we have a language with of this rudimentary kind, with some variables, which might be PQ, etc., and some connectors of whatever kind, but each with its arity, and that's all. We construct formulas in the usual way, a language of this rudimentary kind. Then, okay, we can speak about an algebra of same type as such a language, right? So there's an association between the connectives and the operations on the algebra. And then there'll be a notion of the logic of the matrix. Right? Logic in such a fixed language of the matrix M. Right? So the logic of so we say rule gamma alpha is in the logic of this matrix for every interpretation. So this is just a function from the variables to the elements of the universe here, extended in the natural way to arbitrary formulas in terms of the correspondence of the connectives with the operations on the algebra. For every interpretation H, if H takes every element of gamma to a designated value elements, then H takes alpha to a designated element. So that's the definition of the logic of the matrix AD. So you can say, I mean, if gamma alpha is in this logic, we can say gamma alpha is valid in the matrix AD. Right? Gamma alpha is valid in the matrix AD. And again, it's easy to see from the definitions that if a rule gamma alpha is valid, if some rules in a set H are all valid in a matrix AD, then so is any rule derivable from the set of rules. Right? So to show H does not derive a rule gamma alpha, what we usually show is that every rule in H is in the logic of a certain matrix. Whence every rule derivable from H also is. But gamma alpha, so gamma alpha is not derived. The usual way to show underivability. Okay, well, I'll give some examples, but I'm running out of time, or have run out probably, but examples abound in the abstract logic of this. That's the usual way of showing underivability. I should say these are not usually formulated in these exact terms, but it's essentially that's what's happening. Yeah. So just one last thing here, the level 1 activities. Can I go on for like 5 minutes, 10 at most? Okay. Okay. Level 1 activities. And this is the last level. I mean, it's essentially there's only one activity in this level. This is I mean, the general goal of these theories. In the one case, the more concrete parts of abstract logic and clone theory. In one case, to determine the constitution and structure of a certain lattice of, I mean, they always form a lattice. The lattice of clones or systems. Determine, in the case of clone theories, determine the constitution and structure of a certain lattice of clones. In the case of abstract logic or special abstract logic, to determine the constitution and structure of a certain lattice of logics, for example, all subclassical logics. But a part of this, and important part, is to prove what we might call base theorems. So we show that certain functions generate all functions in a certain clone, and certain rules generate all rules in a certain logic, right? So really, I mean, we might say that we only really know a clone when we have two descriptions of it: a general one in terms of polymorphism, and a concrete one in terms of a particular base in terms of certain functions. And similarly for logics, we only really know a logic if we know a general description in terms of matrices, and a concrete description in terms of generation from a specific set of rules. So these are base theorems, the theorem stating the equality of this kind. So base theorems, and in general, the study of the constitution and structure of a certain lattice of clones. And here we have again base theorems. And the study of the constitution and structure of lattice of logics. Okay. That's the end of this figure. And that's where normal forms come in, right? So normal forms are a key tool to prove base theorems, both in clone theory and in abstract logic. Well, I mean, in the case of clone theory, this is standard procedure. In the case of abstract logic, actually not so much, as far as I know, but I have been working along these lines for some time, and it has proven so far very fruitful, although in somewhat limited range of cases. And I mean, here I have certainly derived as well inspiration from the ordinary clone theory. Okay. I've gone on too long already, so I'll just say very briefly what I mean by these normal forms. So, I mean, take the case of just suppose we're talking about true functions, and we have this set. I mean, what's a complete set? Well, I don't know, versus negation, conjunction, negation, disjunction, negation, implication. Of course, it's one element, a Sheffer stroke, various other things. But with negation, conjunction, and disjunction, we have a very simple construction, kind of normal form construction, to give a representation for an arbitrary function. So I just take the truth table, and right, so suppose we have this. This function, for example, a binary function, it could be, so it's meant to represent any function. Suppose it's this. Okay. How do we construct a form to express this function? Well, we look at the most straightforward way to do it. So look at the T rows here and make the disjunction of the forms describing these things here, right? We can put in some variables here. And this row has a kind of characteristic formula, P and Q. This row has characteristic formula, P and not Q. This is not P and Q, this is not P and not Q. So we take the disjunction of the characteristic formulas of the rows that go to T here. So in this case, we have P and Q or not P and not Q. Or if we want to do something a little more sophisticated, we can look at the F rows. So in the case of this disjunctive normal form, we're saying, well, okay, we're saying this is true in one of these cases, right? That's what we're saying here. This is true in one of these cases. So we can describe the cases, so we disjoin these descriptions. But you can also say, okay, well, this is also saying this is, I mean, the values of the variables are not one of these. This is also another correct description of what we're saying. So we could use that and say, well, okay, it's not the case that P and not Q, and it's not the case that not P and Q. Or, I mean, you can drive in the negation and get a conjunction of disjunctions of literals forming so-called conjunctive normal form. That also works. Of course, other general cases where everything's T, everything's F, so we can deal with that. Okay. But these are the and of course, these forms are all in these set of connectors, not in, of functions, not in order. Okay. So this is the normal form for an arbitrary true function. This is kind of the mother of all normal forms in theory of logical functions. So to prove Bayes' theorems for other cases, other clones, what we do is we take this mother of all normal forms and fiddle with it somehow. That's the usual thing. Sometimes it can get complicated, but sometimes it's very simple. For example, if we have monotone functions, polymorphisms of the natural order relation. This is, I use these square brackets for generation. This was generated by this set and or verum force. How do we show this? Well, take the table for a function, which is, I mean, one side is immediate, right? So this is clearly monotone. But I suppose we have a monotone function. How to express it in these terms? Well, we consider the usual representation, which will involve negation. And now take this usual form, the disjunctive normal form representation, constructed from the table. Now, we simply take, or in general, there will be some positive literals, some negative literals in there, right? So we just strike out all the negative literals. Just strike out all the negative literals. And it's easy to show that this resulting formula expresses the given function, given, of course, the assumption that it is a monotone function. So this is a simple example of how to fiddle with the mother of all normal forms. Strike out all the negative literals. Another nice example is if we have the T-preserving functions. This is generated, for example, by conjunction and implication. Right, so here we have disjunction 2. I mentioned before that we can define You don't even need conjunction. Here you could define disjunction from implication. So here we have disjunction 2 and equivalence, not a mess. Okay, but we don't have negation, so you can't just take the normal form itself. But what do? Well, we can take now the conjunctive normal form. Okay. Conjunctive normal form. So the conjunct will have some form like this: not P1 or not Pn or Q1 or Qn. Right, in general, some negative literals, some positive ones. Okay, but that's not good. We need to do something about this negation. It can't happen, right? What do we do? Well, if I have a thing like that, and it's not in the degenerate case, it's very easy. We just turn this into the negation, this part into the negation of the conjunction, right? The negation of the conjunction. Then I have not P1 and Pn, right? And not this or this is the material implication, right? So this becomes P1 and Pn implies this thing, Q1 or Qn, which is in the given resources, given that we can define the junction. Right? And well, okay, so this works in a typical case where it's not degenerate. We have some things here, some things here. If it's degenerate in that there's nothing here, it's fine. Okay, it's just a disjunction. We have that. If it's degenerate in that there's nothing here, okay, so we have these, just these disjunction of these negative literals. Okay, well, where does that come from? If it's in the CNF, constructed from the table, it comes from the first row. Right? But it is supposed to be a t-preserving function. So in the first row, we don't have t, we have f. So it can't have entered into the CNF. Because what enters into the CNF is the, it's t-preserving. So we have t. Okay. The function is t-preserving. So we have t in the first row. Right. To construct the CNF, we look at the f rows. Right? Look at the f rows. And we take the disjunctions. Right? Okay. That's what enter into the CNF. But here we have t, so this a thing like that will not enter into this conjunction. So this degenerate case will not occur. So everything we need to do, we can do with these results. So this is another nice example of fiddling with the normal forms. That's extremely simple. And okay, this is done not only in theory of clones of true functions, but also clones of k-value functions, modal functions, etc. This is the usual way to show a base theorem. It's to fiddle with normal forms of some original canonical construction that works for any function of the relevant kind. Now, in the case of let me just say just one thing here very quickly. I mean, if it's interesting. One of the things that we have to show when we are determining the constitution structure or the lattice or a part of the constitution structure or lattice is to show certain things are in certain positions. In particular, often want to show that the certain clones covering another clone. It is above, it's not nothing in between the two, properly in between the two. These two are actually examples of maximal clones in the sense that, well, they are not the clone of all true functions, but they are immediately below in the lattice of clones. They are co-atoms in the lattice. And this is actually easy to show. In this case, suppose we extend this thing. We have we have all the functions here, and we add another function, and we take the closure, the defined functions. Right. Okay, we have added at least one function that's not T preserved. Right, so it has f here. Okay. Now we take f, p, everything in p. Right. This function f can be of any airs, right? But we identify all the variables, so to speak. Now this, we don't have f in the first row, right? Since this function is not T preserved. And okay, here in general we don't know what it has, but well, it has to be either T or F, right? If it's T, then we have defined negation, and that gives a. I mean, we have this, right? We know that this is in this clone, so we have these things. So if here we have T, we have defined negation. So we're done. We have already all the functions in a familiar base for all true functions. And okay, if it's F, then we have force. That is also with implication of familiar base for all true functions. Right. So that shows that this is a maximum in this sense. Okay, but let me say just one word. Sorry, I'm going on too long. Just one word about the case of normal forms to prove base theorems in abstract logic. Here, okay, the normal form for what? Normal form for in the case of functions, normal form for the presentation of a function. The normal form definition for the function. In the case of derivation and rules, is a normal form derivation of a rule, or a normal form deduction of alpha from gamma via certain rules. Whenever alpha, indeed, whenever this is really in the logic in question. So suppose a main case, of course, is classical logic, and again, I'm telling you to look at classical logic with these connectors, negation, conjunction, disjunction. What's a canonical deduction of alpha from gamma whenever alpha falls from gamma in classical logic? Well, first, we know classical logic is finitary, so in some sense we can consider just a finite set, gamma naught. Right? How do we do the deduction of alpha from gamma 0? What are some natural canonical rules that permit the deduction of alpha from gamma 0? Well, first of all, of course, we can introduce the conjunction, right, of gamma naught. So we have one formula. Then we have alpha at the end. We want to get to alpha. This here. So we have one formula, and once we get to alpha, and this really falls in classical logic. First, we do some steps of reduction to a DNF. So some disjunction of conjunctions of literals by familiar rules like distribution of conjunction over disjunction and vice versa, the Morgan, double negation, elimination, such things. And similarly, I should say, yeah, I'm thinking of schematic rules because we don't really need to eliminate double negation, right? Double negation can be inside the formula. We have some scheme of permitting the elimination of double negation inside the formula. And similarly in the other cases. There's a really rule schema and there's a canonical base. Okay, do the same thing bottom up with alpha to get to the CNF of alpha. And okay, well, that's then a conjunction of disjunctions of literals. Right? But conjunction of disjunctions of literals. Okay, this we'll get by conjunction introduction. Conjunction introduction from these things. So we have here DM, D1. Okay. So it's enough if you can get each of these from this thing by some reasonable rules, right, to obtain a canonical base. Well, but this is a very simple situation. We have a disjunction of literals here, and here we have a disjunction of conjunctions of literals. When does that? I mean, note that this is equivalent, classically equivalent to alpha. This is classically equivalent to the original formula here. So, since this was supposed to imply this, this still implies this, and therefore implies each one of these. So this indeed implies this in classical logic. How can that happen? Well, there are a few cases. This could be tautological in the sense of being a disjunction of literals containing opposite literals. P or not P. Or then, of course, it will classically follow, even independently of what that is. Well, if that is not a tautological disjunction of literals, then here each disjunct must be either contradictory in the sense of having opposite literals down in the conjunction, or must have a literal in common with D1, right? So if D1 might be, say, Q, and here you might have P and not P, or Q and R, something like that, right? And it follows because this is a classical equivalent to just this. Q and R implies Q in classical logic. So what sensible rules can we introduce to do this? Well, excluded middle is one. To deal with the case where we have tautological disjunction here. With excluded middle, we get the negation of a thing like that. It doesn't matter, there are other literals. We get the negation of that. The negation is not P and not P. We get this from P or not P by De Morgan, double negation. Right? So with excluded middle, we get also the negation of a thing like that. Now if you have disjunctive syllogism, we can cut it. Okay, we have negation of this, we have this or something else, and we go to the something else by disjunctive syllogism. Okay. So there remain the case of these disjuncts here with literals in common. Well, then we can strike out the literals by distribution and conjunction elimination. Right? They have this derived rule, which I call deletion, from P and Q or R to, P or Q and R to P or Q. And this can be derived from distribution and conjunction elimination. Right. So it's P or Q and P or R. So conjunction elimination P or Q. So this will allow, with excluded middle, disjunctive syllogism, and these are the usual rules which we use also to do the reduction to D and F, C and F. Will allow the deduction. So this, I mean, I've only sketched this, but this is a set of rules of this kind that I would tend to consider to be the canonical base for classical logic. And this would be the canonical construction of a derivation for any derived rule from these rules in this canonical base, just like this construction of the DNF or CNF from the truth table is a canonical construction of a representation of an arbitrary true function from the standard base with not and or. And then for other cases, so this will be the mother of all normal forms for derivations or deductions. And then for other cases, what we do is fill it with this normal form. Yeah, I guess a little complicated, but okay. I have managed at least to deal with quite a few logics in this way. I mean, I've been considering especially logics between classical logic and the standard relevantistic restriction of classical logic known as FDE, or first degree entanglement, or burn-up-down logic. And in many of these cases, we can obtain Bayes' theorems by fiddling with this canonical normal form deduction. In particular, I mean, so just to give one example, FDE itself is very easy to deal with in these terms, because all these normal form transformations here and here, and of course conjunction introduction, this is all fine in FDE just as in classical logic. It's in this middle portion here of the deduction where we pass from this disjunction to a disjunction of literals that FDE differs from classical logic, and differs in a very straightforward manner. Very straightforward manner. In classical logic, there are these three cases. This can be tautological, or if it's not, then each one of these is either contradictory or has a literal in common. That's the criterion for transition in classical logic. The criterion for transition in FDE is simply, well, I mean, this FDE implies this if and only if each conjunction here has a literal in common with D1. D1 being tautological cuts no ice, so to speak. Right? It's no good. This doesn't help. This D1 being tautological. Also, a conjunct here being contradictory doesn't help. Doesn't help. There is an FD implication here if and only if every disjunct here has a literal in common with the disjunction down here. So of course, if we take the base I sketched for classical logic and omit exclude middle and disjunctive syllogism, we get a base for FD by its similar argument. Everything else is the same. And here, I mean, if you come to a thing like that, and this was supposed to imply an FD alpha, so this will imply each of these, this will imply this, so there will be a literal in common. So we can get from this to this, in each case here, there will be a literal in common. So we can get from this to this just by distribution, conjunction, elimination. This gives a base for FD. And yeah, I mean, in some intermediate systems, I mean, there are some famous intermediate systems between FD and classical logic. One is a so-called logic of paradox, or LP. And another is a kind of dual of this logic known as a strong clean logic, or K3. So LP is a paraconsistent logic that doesn't have non-contradiction, or has contradiction only called limits. K3 is paracomplete, doesn't have excluded middle. So you could expect that there will be a similar transition criteria, and you get a base in a similar way, right? Because for in the case of LP, a contradiction here cuts no ice, but a tautology here does. In the case of K3, it's the other way around. Yeah, tautology helps, but a contradiction cuts no ice. Sorry, the contradiction helps, but the tautology cuts no ice, right? Tautology, we don't have excluded middle in K3. So you know, in LP we have excluded middle, but we don't have disjunct syllogism. Don't have non-contradiction. In K3, we have non-contradiction. We have disjunct syllogism, but we don't have excluded middle. You can see how it should be easy to transform this thing to give base theorems for K3 and LP. In the case of LP, we just drop disjunct syllogism from the standard base I described for classical logic. In the case of K3, we can't quite just drop excluded middle, but okay, some other easy adaptation will work. Okay, so yeah, I mean, I hope this gives some idea of what I see as very extensive similarities between these two subjects. I mean, there's really said to be twin subjects, right? The complementary parts of I don't know, that's pure logic, and this twinship can be exploited. I mean, it appears in various familiar things and can be exploited further in less familiar territory to as well transfer ideas and results even from one of these subjects to the other. I mean, often things are naturally arise in both subjects, but sometimes something appears at least more clearly or more naturally on one side, and then keeping this twinship in mind can be helpful to obtain interesting developments on the other side. Okay, I'm very sorry. Oh God, I'm sorry. You should have stopped me. I went on for. Sorry, I didn't know I was so late. But okay, sorry. Thank you very much.
Thank you, Rodrigo. Some question or comment? Okay, thank you again.
Okay.
Well, there is a pause for lunch. We go back 2:30 p.m. start the afternoon section with the talk of Alfredo Freire from UNB. He'll talk about implicit definitions, theory, and the issue of categoricity. Thank you, Alfredo.
Thank you very much. Thank you for the invitation. I'm glad to be here. And I'm going to discuss things that were already widely discussed in John's mini course and Rodrigo's mini course, but I'll add some information to the discussion, especially in relation to a conception of foundations that is based on how expressive theories are. So, so let's start with this idea, this problem that everyone here have heard repeatedly throughout this week. We have implicit definitions are definitions done by theories. So when we theorize, we are defining, and we are defining, we are theorizing. And this is actually the robust way of thinking of a definition in a first order environment, right? Because every other kind of definition is eliminable, right? You can eliminate them. You cannot eliminate the idea that you should start from a theorization. And this is where you get the meaning of the basic terms of an idea, a concept, or anything like this. All right, so this is again repeating myself, but maybe it's so important that we need to repeat lots of time. We don't have, because of various theorems, Loven-Heiskollen, Gödel's, and so on and so forth, we have a difficult time finding isomorphic types for theories. And this is a profound threat to objectivity. As, for instance, Rodrigo had discussed quite a lot. We have to have a basic semantic agreement in order to understand our activity in some way objective, as if we are talking about one thing or discussing something that we have a grasp on what it is, right? So how can we say that we are talking about the same objects? All right. Not sure what's happening. All right, so this kind of failure leads us to consider some alternatives to how to deal with definitions, right? Because we want to fix the domain that we are talking about, and we have some conceptions, right? The first one is what I believe Rodrigo is pursuing, which I find extremely relevant. But there are also two other approaches which I find complementary, and I think these three approaches are actually the proper way to understand the definitions. It's a dialectic between these three approaches. The first one, as we discussed, is the idea that we fix the meaning through some other means, right? Through the mathematical practice. So we have non-formal means of accessing what are the natural numbers, and we refer to them in our theorization so that we have a better grasp on what we are fixing with our theories, right? What we are discussing actually, right? So this is what we discuss at length in Rodrigo's course, the idea that we refer to the natural numbers, and by doing so we can understand that we are incorporating lots of, we are putting aside much of the problems of categoricity that we have without them. So this is basically something that is quite interesting as a strategy in general, which is to refer back to some kind of what is the name of it? It's a oracle, some kind of oracle, right? Like you have this can be thought of in relation, for instance, to computation, right? Like we have lots of non-computable functions, right? We have non-computable functions, but you can think that for some problem you have an oracle that you can access, right? So in this way, you're not necessarily cheating, right? Like you're just understanding what these, to know precisely these computations can give me to compute other stuff. So it's a relative kind of agreement on what we are pursuing, right? So this is it's a very interesting approach. The second approach, which is one of the approaches that I mostly have worked with, is to try in formulating and working with some kind of partial notion of categoricity. So good idea that we are actually talking about something that is distinct from simply taking algebraic theories, right? Like we're talking about group theory. You're not intending to have one single structure. You're intending to have lots of them. But maybe there is a good idea on what it is to have a small number of structures. Of course, it's not going to be about numbers at all, because the number of structures will be exactly the same. But there is, when you look for a partial idea of categoricity, you're looking at fixating a smaller in some sense conception, right? Like smaller in some sense. These ideas of partial categoricity, for instance, the first instantiation of it were in Zermelo's work, where he realizes something that is very easy in set theory, that the hierarchy grow ever larger. The hierarchy of sets grow ever larger. But, and so when he talks about the categoricity, the second order categoricity for set theory, he talks in terms of fixing up to some cardinality the universe of sets, right? This is not actually what's going on here, right? This Zermelo style of thinking of a notion of categoricity is much more like this one, right? But instead of relating to the natural numbers, he is relating to the idea that the concept of power set is transparent in some way, right? Like the concept of power set is transparent, so it's basically this that is happening when you have the categoricity for the Zermelo categoricity for set theory. It's that he is considering that the concept of power set is the actual concept of power set in some way. So exactly as, for instance, Rodrigo have worked, in the sense that, all right, so the conception of numbers actually refer to the concept of numbers, right? So it's a similar kind of strategy, but it's the strategy of referring to second order logic, which most of us, at least I believe, think is too much to do, right? It's to think that we have a clear grasp on what it is to jump from the first order theory to the second order theory, the full second order theory, is too much to believe, right? Like maybe it's too openly Platonic to I don't know. I mean, maybe you believe, but the point is, it's hard to simply assume this without any without further consideration, right? And there is the third one, which I will briefly discuss by the end of this talk, which is finding alternative ways of understanding definitions. And this is quite interesting because it relates to something that occurs in the logic metaphysical literature, which I find quite important.
and I think we should consider it more in connection to the idea of the clarity of a concept, which is based on this recovery done by Kit Fine on the idea and the conception of essence, right? So, so in basically what you're saying, that the concept is not necessary. I think Rodrigo actually touched a bit on this, but let me rephrase it a little bit. The idea that defining is not necessarily talking about its position in the structure, right? So it's an anti-holistic way of thinking of a definition, right? So basically you can argue that a concept is not does not need to refer to the whole universe in order to be understood. This, as a matter of analogy, is what Rodrigo in his mini course has said about we are fixing the concept of being the successor, right? So this we can understand the idea of the idea of successor without actually having to know to have some actual grasp on the full structure of numbers, right? So you can have a perfectly good idea of a definition without referring to the holistic universe, right? So this is the third conception I want to consider in this universe of mathematical defining, right? All right, so let's continue. So here, discussing briefly what I already said, I like this style of dialectic that Putnam puts in his work on foundations of mathematics, which is the idea that different kinds of approaches to a mathematical concept can produce the dialectic that is related to the grasping of this concept. So this is kind of the style that I want to present here, that it's approaching definitions in this tripartite style, but I think you will have a good grasp on what mathematical definitions are. So first, mathematical definitions referred back to, and I'm following in the first one completely on Rodrigo's approach, referring back to some transparent notion, right? So you refer back to a transparent notion and you understand things in relation to this transparent notion. And then, of course, you have philosophical arguments for why this is a good transparent notion to be considered, right? So this is the first one, and this is different from considering what are good ways to approach partially the notion of categoricity, and how can we understand these ideas, what differentiate. For instance, there is a very interesting and quite familiar intuition that all right, there are many models of natural numbers, but there are not that many. You know, it's not that open. You know, they have a fundamental structure going on there. So it is, in a sense, even in the first order sense, somehow different from field theory, groove theory, and so on and so forth. Right? And trying to capture this difference is what the second approach aims at. And the third one is to think definitions in this very traditional, actually, way, which is the way of Aristotle, right? Like, Kate Fine recovers this idea that to understand what a concept is, or defining a concept, is to investigate its essence, right? And in investigating its essence is not to understand what are the necessary the necessary consequences of it. So it's not holistic, it's constitutional, right? To understand what a person is, I do not need to refer to this person being, I don't know, being the member, that's the example he gives, being the member of the singleton set of it, right? This is a necessary concept, this is a necessary consequence of it, but it is clearly not constitutive of what the thing is, right? So it's an anti-holistic approach to definition, and these three things in conjunction, in my view, are important to understand the concept of mathematical definitions, right? So here, let's, as I told you, I will focus on the later two ideas, more on the second. And the first is to try to formalize some kind of partial notion of categoricity. And the first one that appears in the literature is the idea of internal categoricity. Here I put this all of three because of in the following sense. Parson is the first one to refer to the concept in some way, but he haven't named the concept. Well, I don't know how to say this name. Walmsley in 2002 coined the name, and Van Anen has worked a lot on it, like published many papers on it, on this concept. And there is the concept of tightness. The concept of tightness was first introduced without naming by Albert Visser, and later well studied by Enayat, and it's currently being very well investigated. So first, I'm going to attack the first version of it, and actually, it was during the seminars of Rodrigo that I realized that it is okay to attack this concept because there is a way of recovering it in the end, right? Because otherwise it would be too much just complaining randomly about a concept. But I think it's a grave mistake in the first order sense, but it can be recovered if you have a different notion of axiomatization. Let's dive into the problem of internal categoricity, right?
I just said that Van Anen's axioms are second order. He's arguing for internal categoricity of second order.
Yeah, but these are all second order approaches that are perfectly internalizable in first order logic. These are not full second order logics, and all of his results can be done in first order. I've done it in a paper. Yeah, because it's important because, I mean, second order set theory is already categorical. So, I mean, it's first order theory that is not categorical, so you need a slightly weaker version of categoricity to obtain it, right? Well, but it's okay. I'll try to explain a little bit of it later here. But all right. So this is a tentative definition. I try to write in a more streamlined way. If you don't understand, I'll try a little better. But the idea is that you have two versions of the symbols for the theory, right? And then when you have a model containing these two versions of the theory, satisfying this theory in these two versions, then these two versions will be isomorphic, right? So let me go through with an example here. So the easiest example is set theory because, of course, set theory has a very simple language. So the idea of internal categoricity is to consider two versions of a theory. So ZF with membership 1 in the language of the two, and you have this also in the language of the two, right? So these are extensions of language extensions of ZFC in this language extension of this ZFC extension. But there is a trick here that occurs implicitly, which always troubled me. But now, which is, and that after you have this, what you will have is you consider like a model for the two theories, right? And then the second membership satisfies the second one, and if these conditions are met, then they are isomorphic, right? But that's the thing, that there is something weird going on here. And the something weird going on here is the fact that how can it be that these things get connected? How these things are connected through satisfying two different theories? I mean, this language extension should not be should be somewhat neutral to what's going on. It's because it's not actually neutral. This theory is not simply a language extension of this. It's a language extension that, most importantly, affects the way you understand the axiom of separation and replacement, right? So, right? So the trick here is that this formula here in the schema is in this language, right? So this is something that should, at least in my opinion, raise an important question mark, which is, all right, so when you think of this way, first of all, of course, it's not anymore the same theory in a sense, but this is not even the important part. The important part is that now it matters how you axiomatize it. Right? This is the important aspect of it. It now matters how you axiomatize, because it's only in the schemas that the formulas are in this double language, right? So the first question that popped into my mind when I saw it was, well, but I mean, if I axiomatize it differently, would it preserve the result, right? And this is something that I had in my mind for a long time. I did not bother that much, but this week I realized that there is a very simple example that showed this property. Internal categoricity property is not preserved under theoretical equivalence. So, I mean, this cannot be a good notion, right? I mean, in my opinion, this is something that I learned as a student from Rodrigo. He insisted very much on if a property, if a meta-theoretical property is not preserved under logical equivalence, I mean, this cannot be a good property. This is a simple idea that is very powerful when you're considering some intricate meta-theoretical properties, right? So, do you have any questions about it? Because any set. This is the axiom of separation.
Oh, okay. Right, sorry. Yeah.
It's just that if I kept writing, it would be below the. Sorry for this, but this is the axiom of separation. And the thing is, the connection that allows us to obtain this result is obtained actually by the fact that the axiom of separation becomes an axiom connecting these two languages. So when these structures satisfy each of the versions, it is satisfying a whole bunch of formulas in the extended language. So you're adding lots of axioms. But then the most important part is that now it feels like it matters how you axiomatize, because if you change a different kind of schema, now, do you know that this theorem is preserved? You don't know. You don't know if this new axiomatization is internally categorical, because you're fixating on how it's written. The theorem that says that ZF is internally categorical is connected to the way it's written, right? I mean, this is not a proof that this is a problem, but it's at least gives you the feeling that there is something fishy here, right? All right. So I'm going to just present a proof sketch of how you can prove that this is not preserved under theoretical equivalence. And the idea is actually quite simple. The idea is to start with NBG. NBG, the class theory, which is known for being finitely axiomatizable, right? And you define the NBG star by adding to NBG the following axiom. Basically, what you're saying in this axiom is that for any class that satisfies the finite version of NBG with this R in place of the membership, then this relation will satisfy the comprehension axiom. This is simply logic, right? Like this is a simple logical consequence of the, this is simply a logical consequence, actually. So this does not change the theory. The theory should be exactly the same, because I just added a logical consequence. But now, observe that this logical schema here, this logical schema here is now, this logical axiom is a schema. And as a schema, it will make us obtain the isomorphism. Because basically, if you think about there, the set theoretical part will be isomorphic, because exactly from the same reasons that you obtain here, the isomorphism. But then, because this is a schema, this here will be in the double language. And because this is in the double language, when I put the copy of the second one here using the schema here, I will obtain a copy of the membership too. Then I can use this copy here. This copy will definitely satisfy the axioms of separation and will satisfy this. But then you obtain each of the missing classes that correspond in the isomorphism with the classes of the other, right? So in this way, what you obtain is internally categorical theory that is equivalent to a theory that is not internally categorical. NBG is not internally categorical. This is easily proved. And actually, I will not prove it because this is a simple consequence of a later theorem that I'll talk about. All right? So what you have is like two different axiomatizations. One is internally categorical, the other is not. And all right, this means that there is something weird going on in this conception, right? Even though it's widely used. And the thing is, actually, it was recently that I realized, actually, I mean, so many people are using it, there must be something going on, right? So even though I had this intuition, I haven't bothered to try to prove that this is a problem, only recently, because without even having the proof, I mean, this is already very odd for me. But then I started realizing that a different conception of axioms can make you recover the idea of internal categoricity if you think about the axiom schemas as a single axiom. If you think of them as single axioms, then for instance, in the style that Rodrigo has presented us here, if you think of them as single axioms, then of course they are internally categorical because you cannot break it down in different ways, the axiomatization. The axiomatization is connected to the meaning of it, right? And you have also, this is something to work further, which is like, oh, how these, can we have schemas? So in this style, if you think in this style, you have first order equivalent theories that will not be equivalent when you think of the axioms as these omega axioms, right? They will not be equivalent. This is also evidence in this regard, which is kind of interesting, right? Like there is something special about the way we axiomatize the theories, which is something that goes in actually the third direction, right? Like the essence of the theory maybe is connected to the way we axiomatize it, right? So this is a problem for a first order conception of categoricity, but not necessarily for an omega conception of categoricity, right? The second way, which is for which we have many recent results, is this concept of tightness. This concept of tightness is connected to the idea of bi-interpretability. Bi-interpretability is connected to the idea that two structures are, one can interpret the other in such a precise way that they are actually the same in the sense of expressiveness, right? Like this is the way I at least think of it. Right? Because when you have two theories that can interpret one another, there may be some things that are missed when you go back and forth. But interpretation is a further property that guarantees that you're not losing information. This is what's important to understand in this talk, right? So basically, a theory is tight, so in the sense of having few structures, right? So it has few structures. It's not having one, but have a small number of structures. It's not a number. It's a smallness in a different sense, but I think it's an important sense. So a theory is tight if any two bi-interpretable models of the theory are necessarily isomorphic, right? So each bi-interpretable class of structures of the theory are unique, right? All right. So first of all, this is easy to prove. The tightness property doesn't have the same property that internal categoricity has. Any theory is tight if and only if their theorems are tight. So everything connects to the whole collection of theorems. Everything is the same. So there is no problem of different axiomatizations, and it's also upward preserved. So if you have extensions, a tight theory continues to be tight if you add axioms. Adding axioms don't affect the tightness of a theory. All right. Sorry. So there is a collection of very interesting results, which I give you here. It's actually NIAT, which has worked a lot on this issue here. He insists on having like a collection of properties. I mean, I think the most important one is tightness. There is some asymmetrical ones and stuff like this, which he calls solid and neat and so on and so forth. I like tightness, and that's why I consider tightness the most important one. It's the strongest one. And all right, so Visser has proved that piano arithmetic is tight. Then NIAT published that ZF is tight, but then Visser and Friedman told him they already had the result, and NIAT believes him, and all of these were discovered when Joe Hankins and I published in a web post that we had the result. So it's like it's a nice feeling, right? This is something that occurred when I was in my PhD, that you're working with that's something that is in the zeitgeist, right? Like the zeitgeist of the time. But also NIAT has proved that second order arithmetic in this first order sense, let's not confuse it, like understood in this first order sense. So it's basically saying that you have the power set of the power. Yeah, choose sorted first order logic, and more Skelly MK, the second order set theory is also tight, right? So these theories are basically what we expect to have this robust sense of categoricity, right? And if you have weaker theories, like it's very simple, for instance, to prove that a group theory is not tight, right? It's very simple to prove a whole bunch of sorts of things that are not tight. But most importantly, there are many theories that fails to be tight, right? So if you remove the replacement axiom, ZF loses the tightness property. It's quite intricate to build these proofs on non-tightness. It's very tricky because you have to find bi-interpretable theories that are not isomorphic. So it's like a very fine-grained work of building structures, right? For this first case, we have appealed to a weird construction by Matthias, which is called slim models, right? It's a technique that he mentioned to me and Joel that he published this technique to show that it makes no sense to work on ZF without replacement. So it's just a toy example, but it was fundamental to obtain this result. It's important. We extended the technique and applied to obtain this result. These are the one is very complicated, and it uses some forcing for these ZF theories without power set, and it's very complicated and boring. This first one is much better. This one is more weird. But then together with Cameron Williams, I proved that for the second order versions of these theories, any subtheory is not tight. No subtheory is tight. So it's basically it's strongly minimal, right? It's not only minimal, but I mean, you cannot remove anything, right? NII has also proved that every finite subtheory of ZF is not tight. And recently, Gruza, I don't know how to say these two names, sorry, but it's Mateus. I call him Mateus. But these theories are... Are you sure? Yeah. All right. This subtheories, there are subtheories of PA and Zermelo-Frank which are tight, but remember, you know, if you consider, for instance, the axiom of replacement actually as one single axiom, then no subtheory of ZF is tight. It's only when you have like these very complicated arrangements. Actually, the arrangement they do is basically to consider all the axioms of ZF without the axiom schemas, and then add all the pi1 consequences of the theory. It's basically this idea. You add the pi1 consequences of ZF. All right. So yeah. So this is for me quite interesting, right? Like the idea that you have tightness acts as kind of a way to measure ontological commitment. It's measuring how much a theory tights the universe of structures up to the conception of expressiveness, right? So it's like yeah, it makes it. I'm going to give in the next slide what I consider the best interpretation of this, which is connected to expressiveness. But this is something that I have discussed at length with Hugo, which is the idea that there is something quite interesting about these results, which is like these theories are exactly where the axiomatizations have stopped. Right? How weird it is that they are actually very minimal in this sense. And it was not built to be this way, right? Like this concept was not built to obtain this precisely. But in the end, this the theories that have this property in somewhat a minimal sense are precisely this, right? For the second one, order ones, they are definitely minimal, but the first ones are minimal-ish, but minimal. But the thing is, like, we have stopped precisely at these axiomatizations. So basically, you can say that we have stopped when we have defined the subject, right? You can think of it like this. All right, it's when we got to these conceptions that we have defined in this, at least this first order sense.
If you add axioms, you keep the tightness.
Yes.
It's preserved. So how can you say that they are like, you could add some axioms, yeah, and they still, but maybe will capture.
But that's the thing, you know, the idea is basically to say, well, before we reach those axioms, and for ZF, this is quite familiar, right? Zermelo didn't have the full axiomatization, at least not in a first order sense. He missed the foundation axiom, he missed the replacement axiom, which is quite important in this context. And after that, every discussion is basically an experiment. No one agrees to add any other axiom to ZFC, not even C, right? But this, whenever we present this series, this is the theory, right? Before that, something is missing to the standard axiomatization. And after that, no, it's only about opinion somehow. I mean, we can live in different universes somehow. And at least the disagreement is not about, it's not as much about what is the subject, but what is true about the subject. That's what I'm saying. You know, like it's when you reach somehow axiomatization, now we're talking about the subject and everything that goes besides, that goes beyond these axioms may be understood as disagreements, philosophical disagreements about the subject. But the subject was fixated by this first order investigation, you see? So the important part is the minimality, right? And the fact that adding doesn't lose the properties is important too, but I mean, it's not what we're looking for. And it's kind of, this is something that I have thought about, which is quite interesting. It is the idea that when you still think there is hope to get to get categorical theory, you think you have you can add axioms, right? But once you realize no, there is no way to get a categorical theory, now you can change your mindset and saying like, oh, maybe it's good to understand what is the core, right? So it changes the direction, right, of research, in my opinion. Of course, you can disagree. It's too slow. All right. So just rephrasing it, a site theory cannot be satisfied by two different bi-interpretable models, right? If two models are bi-interpretable, they are isomorphic. If they are different, they are not bi-interpretable. So if you consider that you have mathematicians that agree about what is the structure of set theory, right? They are disagreeing about this fixed concept that they agreed on, right? Like they agreed on what is the subject. But now because you have a tight theory, you know that this is fundamentally connected to a semantical agreement. Because if they live or think about different models, necessarily one of them is losing something that you can express in your model. Like that's the kind of message that you get if you analyze it. It's basically like this. Because of these results, I mean, there are some others related to it, but the basic feeling is that if I have a model in my mind, you have a model in your mind, if they are different, I definitely cannot see the whole universe of structures that you can see. So we are actually living in a different mathematical, in a different semantical agreement. We don't live in the same world, right? So basically you're saying it's categorical in this sense. We have to agree that we live in the same world. If we're talking about ZF, we have to agree that we are living in the same world. Otherwise, we will miss stuff that is expressible by the other. Right, so you can think this way. All right. So how much time? So all right. So now that I passed through this second characteristic, let's dive briefly in the third way of approaching, which is one that I am investigating currently, but it's in this initial phase, and I'm still. So it's mostly philosophical without mathematical results, but there are important aspects to it which I find important to consider in connection to definitions. The first important aspect is that ZF is fundamentally an open ontology theory, right? So what this basically means is that if you fix the meaning of the quantifiers, you're necessarily losing sets, right? If you fix the meaning of the quantifiers, so I'm talking about the subject in a slightly phenomenological sense, in which, like, if I work as if the meaning of the quantifier is fixed, then I necessarily have agreed that I'm losing some sets, right? So we know that we are always constantly making this trade-off, right? We fix the meaning of the quantifiers in order to work semantically, but then we know that we are losing sets, right? So the message I get from this is something that is connected to some of the discussion that happens in the current literature. There's too many people nowadays talking as if talking in a multiverse theory of sets, because of course there is no one single universe of sets in many senses that you can think of. This is not up to discussion, actually. I mean, it's up to discussion, but I mean, no one believes that there is a model of set theory. It's always, at least you have more sets, right? It's basically, what is your multiverse theory of sets, right? But this is especially problematic, for instance, in Steele conception of set theory, which is followed by Toby Meadows and Penelope Maddy, which is to say that in studying the set theoretic multiverse, what you're doing is fixating provisionally the meaning of the membership. So they are assuming from the start that to discuss the meaning of the membership is fundamentally connected to fixing the meaning of the quantifiers. So it's fundamentally holistic, right? You can only understand, it's the idea that it's not provisionally understanding what are the universes of sets. This is a different conception, right? Instead of saying, like, we understand what membership is, we are just discovering new sets. They're saying, like, no, we don't understand what membership is, but we know what the sets are, what are the sets, and we provisionally go about discovering the refine the meaning of the membership. So I think it's a complete weird commitment to this holism of meaning, right? So this is something that I find quite interesting in this third conception, this conception of understanding operations in relation in connection to the concept of definition and essence, right, as Kit finds us. So this is apparent. For instance, there is this paper of Maddy and Meadows in which they discuss this disagreement between wooden and steel, and basically when they are discussing amalgamation of the multiverse, the amalgamation is basically if you have a forcing relation, there is a forcing relation that connects both universes that you have obtained. In Wooden conception of the multiverse, he doesn't have amalgamation because he thinks that you do not have access to to all possible partial orders. So he's going into more in the direction of what I'm saying. You know, you're losing objects. That's why you cannot access, maybe you cannot access this amalgamation. And still goes the other way. He thinks that you should not think that you're dealing with discovering sets. What you're dealing with is building a theory of the multiverse. You're building a theory of the multiverse, and because you have the theory of the multiverse, amalgamation will come. So there is this discussion in the literature about how to conceptualize the universe, and I think Wooding is more right. Right? Let's not. I'm talking about being non-holistic here in the sense of the meaning, which is basically trying to say that in conceptualizing the open-end universe of sets, you should be more prone to consider that you do not have obtained the whole universe, instead of saying that you do not understand the meaning of the definitions. Right? That this is the subtle difference, which I think, which here, that's the important part. That's why I put this example here, is to say that there is an actual discussion that bears to this subtle disagreement, right? One thinks is about theorizing the conception of the multiverse, and the other no. So here I'm just repeating this very same point. Sometimes this happens in presentations, right? You advance in what you're saying, and this is the exact it's the exact content of the next slide. So here, one last comment here, and this is connected to a graduate course that I managed this semester, in which Luisa was there with me, helping me with the course. There is something interesting in this historical discussion in the beginning of the conceptualizations of logic. And this is quite interesting, that Freire was very much concerned with the idea that the quantifier has to be unrestricted. Quantifier has to be unrestricted. And this is something that struck me. Why he is insisting on this? And this becomes apparent when you read some of the letters between Freire and Russell, in which Russell tries to say, no, your program is not finished, and Freire responds, no, it's completely finished. There's no hope for it. And the point, and then I started investigating, like, why he's so unhopeful, right? I mean, we know from things that come later, but at that point, no, it's not that simple to say why he was so unhopeful. And the thing about this unhopefulness is that he realized that in order to build this ontology, this logicist ontology, he would have to subscribe to axioms that are by their nature restricted, like to this conception that the universe of concepts is restricted by some formal consideration. So this for him was a sign that the concept is not logical, right? So like this type theory that Russell is doing is okay, but it's not logic anymore. So he realizes this before Russell, right? Like, this is not logic because you're being too specific, right? So there is something, and the lesson you get from this is that All right, so logical concepts have to be connected somehow to unbounded quantifications, right? And there is something about it, Luisa, I don't know if you remember this, but the first article on type theory by Russell, he has a whole section, this is quite funny, a whole section where he tries to argue that there's two kinds of quantifications. Do you remember? Like a quantification that is unrestricted and a quantification that is not. And so in the beginning, Russell was still like struggling with it because there is this quantification that is unrestricted and the other one which is restricted to the subject. And the argument Russell puts in this paper is saying like it says excluded middle cannot be restricted. You know, it has to be all proposition, but all. You know, you do not have all of some kind. It's all. All phrases are subject to this. You know, it has to have this feeling of unrestricted quantification. So it's in this sense that I argue is a very strong word right now, but it's I'm just putting forth some of the ideas I've been thinking about this third conception, which is that membership has a logical aspect. Membership has a logical aspect and a mathematical aspect. So it's different, for instance, from equality. Equality may be considered a full logical relation, but maybe membership it's in between, right? It has some feeling of unrestricted quantification, because what is a property to be connected to unrestricted quantification is that it is connected to a unbounded quantification. I'm committing to the meaning of it, even though I don't know all the instances where it presents itself, right? So I'm committing to the meaning of membership, even though I do not know enough about large cardinals, right? Like we don't know. Maybe the fact that you are discovering new sets will not change. Will be compatible to the meaning I currently have, right? So this is the logical feeling of the membership connection, the membership axiom, and but there is a mathematical aspect to it, which is the fact that you cannot do too much without considering the sets that exist. So there is like this double layer of mathematical aspect and logical aspect. You're committing to things that are beyond the semantics of your quantifiers, that go beyond your quantifiers. Different, for instance, as in numbers. When you're talking about number theory, what you're talking about is a collection of objects. Is there? You know, there is no further. There is no, at least mathematically, you can say that there is no numbers being discovered. They are there, right? But when you're talking about the universe of sets, there is no conception of totality. So you're always committing to something that goes beyond your quantifiers. So this is what I'm saying. There is this is a logical aspect of the membership relation, and the fact that most of these of its important meanings comes at hand only when you have existing sets, right? So, I mean, I'm sorry, it's an exploration, so it's still not well fully developed. To complete this sense, you know, this is something an analogy comes at hand here, which is something quite interesting to think about, because it's quite similar to membership. If you consider the analogy of human beings, you know, if you think of human beings, do you know the meaning of human beings? You know what a human being is. I mean, if you have to know all possible human beings before you can say that you know what a human being is, then all right, you can be holistic about about any meaning, right? But there is a sense in which we understand what a human being is. I do not understand all the consequences, all the possibilities of it, but I understand the concept. The concept is categorical. So it's similar to the idea that Rodrigo tried to put here in the mini course, which he says, like, I understand the concept of succession is fixed. I do not have to have the whole function to say that the concept of succession is fixed. So you can think of concepts in this sense, in this non-holistic sense, right? So you can grasp the concept and you can say that you understand the consequence even though you don't know all the necessary consequences of it. This is the change in understanding that you get when you consider this non-electic metaphysics, right? Like these metaphysics that are considering not only the necessary and possible, but also the essential properties of the things considered, right? So this is it, I think. Yes, this is only the references. I'll try to I don't know what I will do with this presentation. Maybe I'll publish in the internet or not. Anyway, thank you.
Alfredo, some comments and questions?
We might want to just chat more about this later, but where does the categoricity that I was talking about?
Sorry, I couldn't.
I'm sorry. Okay, yeah. I gave this argument about an extension of the omega rule that gave categoricity for arithmetic.
Yes.
How does this fit in?
Yeah, that's the thing, you know, like that's what I discussed in the beginning. You're doing like this relative categoricity because when you're doing the omega, when you go to the omega world, you are fixing some parts. You're fixing the interpretation of something that is not first order formalizable, and understanding, which I think is brilliant. You know, like as I said, you expand the comprehension of the universe. You're fixating the idea that you have full transparent access to first order formalizable concepts, and you're investigating what are the other things that become fixed by considering this transparent. Exactly. Yeah, the first conception, you know, that I try to put in a more abstract light, right? Like you're making this, considering something transparent and understanding what becomes fixed in relation to it. So it's the first consideration.
When you say like the membership relation, it's in a sense logical and in a sense mathematics. Why, can you explain why is still in a sense logical? Why is not only mathematics?
I try to. I mean, there is a historical sense that I didn't put here, which is right. Freire and Russell and many, even other people. Like Hilbert in his text is very funny because he talks about membership and second order interchangeably, and he did not believe that second order was not logic yet, right? This comes later. So it's, I mean, the idea that membership and the logic of concepts is connected is already historically, you can see historically. But what I'm saying is trying to explain it. And what I'm trying to explain is that logical concepts, the fundamental aspect of classifying something as a logical concept is how this thing connects to an unbounded quantification. For instance, why the concept of sum is not logical? Yes. Why? Because there is no sense in which you're committing to the sum of things that you haven't discovered. The concept of sum is connected to the structure of the numbers, and there's no numbers to be discovered. When you're doing a logical concept, you're committing to something that goes beyond your quantifications. You goes further than your quantification. And this happens in set theory because of its open-endedness, right? So if you consider that you understand the concept of membership, if you don't, basically you can also put it like this: if you think like steel, Maddie, and metals, then it's purely mathematical, because you're not committing to anything further than the theorems. It's just that the concept is provisional, because you're not committing to what goes beyond that quantification. The concept of membership is the same even if you discover more sets. That's what I'm saying. That's the reason why it has this logical flavor. Let's put it like this. I do not have a full conception of it. But what I'm saying is that I'm following Freire here in saying that there is something about logical concepts that have this connection to unrestricted quantification. Right? So this is what I'm trying to make as a connection.
More questions? Oh, let's thank Alfredo.
Thank you.
So we are going to the last talk. George will finish our meeting today. So unfortunately, we are in the last talk. Giorgio will close our very nice meeting and very nice week, very interesting week. Giorgio, please. Giorgio is from University of Pisa, and we've joint work with Leon Hosting and Lucas Mauro. Talk about learning on the intended model of arithmetic.
Yes. Thank you very much. I mean, as the last speaker, I have the honor and the duty also to thank the organizers, mainly, I mean, Ugo and Rodrigo and everybody. It was a very nice week and very nice talks. So I thought about presenting something else, but after the mini courses, I thought that this talk actually fit better with the discussion. So we saw in many of the talks and the mini courses that one of the problem is that how to fix the reference of our intended mathematical language. And the idea here is that that besides the reference to practice that came out quite clearly in the discussion, I mean, there's an agreement among mathematicians in order to understand each other, but there's still an epistemic aspect to that. That is exactly, even if there is an agreement, how can we, in the end, converge on what we understand to be the shared idea of arithmetic we have? And this is the idea of the talk. I'm trying. I mean, as Ugo said, it's joint work with Leon Horsten and Lucas Amaro. And the question was, there is a literature and some very nice ideas from learning, theory of learning in general, and we apply this to the case of arithmetic. Let me. Okay, so I'll briefly present the question under consideration and the learning framework that we're going to use. And then the idea is that we try to idealize the relationship between two speakers in trying to single out the intended model of arithmetic. And we will do it through some infinite games. That is where there is a teacher and a student, and just by asking a very basic question about the model that the student has in mind, the teacher needs to understand what is the model that the student has in mind. And this will see how we have three versions of the game, and we'll see how the computability constraints actually help to have a winning strategy in this game of trying to understand the if the model that the student has in mind is the intended model of arithmetic. And we'll have an interesting twist in the very end, because computability in itself is not really enough, but we need something more. So the basic idea is that, this is something we've been discussed at length during these days. So we have an intended model of arithmetic. And it's for also today. It's kind of the first slide of every talk. We have an intended model, but we have some problems, mainly that PA is not categorical, and we have, of course, in general, some limitation in using first-order logic in order to pin down the correct interpretation of our language. But again, we have the mathematical practice can help in understanding this, because it's a matter of fact. We understand each other. We know what an omega sequence is. And so the question is, what kind of epistemic access to the standard structure is available, since in fact we have an agreement on that. And it's important to cite this the Tenenbaum theorem exactly because it seems to go in the right direction, saying that if we assume besides our basic understanding of the mathematical language of arithmetic, that the operations like addition is computable, then there is a way to single out the intended model, exactly because there is no non-standard model that supports a computable addition and multiplication. So, there seems to be a structural way of separating standard from non-standard, relying on computability theory. But I mean, in itself, this is a theorem, and as many theorems, the interpretation can be quite different depending on the philosophical task we have at hand. And I mean, very interestingly and recently, Vannan and Maddy wrote a little book trying to express that the many different ways in which categoricity theorem can be interpreted, and how the use we can have of these theorems in our philosophical problems changes depending on the philosophical goal. And here we have the same problem. So in trying to use tandem bound to give an answer to the problem of determining the model of arithmetic, we have three at least different claims that we could derive from this. The first one is that computability separates standard from non-standard presentation, which seems to be one of the conclusion of the theorem. Even though, I mean, it really depends on where you formalize the theorem, and so I mean, there is always a problem of circularity, exactly because computability and the notion of computability requires some form of arithmetic to develop. And this criticism has been done already, and so that's one specific claim with one that can be assessed. But so the other claim is that computability helps fixing arithmetic reference, exactly, and that's a more metasemantic conclusion. And the third one is that computability supports a method of recognizing standardness, and that's actually what we are trying to discuss in this talk. Exactly. I mean, just to separate the three questions. I mean, I kind of already said that, but so we have a question about categoricity, whether Tenenbaum and computability actually helps really in pinning down the real model of, I mean, the intended model of arithmetic. There is the metasemantical question, which is how do we fix the reference? And well, computability hypothesis seems to help in doing that, exactly because non-standard models do not support computability operations. And then we have this, which is kind of a different question about the recognition. How do we recognize? How do we understand each other? Because I mean, and that's, I think it's an important question, exactly because one way, for example, of understanding the internal categoricity theorems is that these explain, in some sense, intersubjective understanding of a specific notion, without getting into objectivity, but at least an intersubjective access to arithmetic. So yeah, that's just to introduce. So the idea is that in this game between students and the teacher, the answer of the students are governed by one fixed model, and that's the model that the student or the other person with whom we are talking has in mind. And then in questioning and asking basic questions about this model, we can try to understand if it's the standard one or not. So the idea is that we'll have 3 games. I'll present in a moment the specific games, just to give a preview of the results. And so we have 3 different games between a student and a teacher in trying to understand exactly what the model, if the model of the student is standard, and with different set of constraints. And so if we have no constraints on the model that the student can think of or choose in some sense. The result is that we have no winning strategy. There's no way, even at the limit, of understanding whether the student has a standard model in mind or not. If we have some computable constraints, then there is a winning strategy. However, and we'll see in a moment, the winning strategy is not computable, which is kind of strange. Exactly, because if the goal is trying to understand each other, if the goal is to remain in something like a normal interaction between human beings, I mean, non-computability is kind of a big issue. So, but then the interesting part is that if we also constrain the addition to be primitive recursive, then there is a recursive strategy. So if we ask that in our understanding, the way in which you think about the basic arithmetical operation is primitive recursive, not just recursive, which is kind of okay, because I mean the one we learn at school are primitive recursive. Then there is a computable winning strategy. So there is a computable way to understand if we're really talking about the standard model. And this is interesting because I mean the moral of all this is that first of all, but this is an old news. So first order logic is not enough, but then also computability is not enough. We need something more, which is primitive recursiveness. That's the idea. We'll work, I mean, this is just to fix the notation. We work with the language of arithmetic. This is the language, and with models of true arithmetic. So we fix the theory of n, and we have the models we consider are just models whose domain is the natural numbers. But of course, I mean, having the domain as natural numbers doesn't mean to be isomorphic to the natural numbers, because there might be some very strange computation. So that's also important, because I mean the way we refer to numbers from outside might actually be slightly different from how numbers are ordered within the model. Because and that's the thing, because I mean we have a way of presenting the models in terms of course the labels that they have, because they are isomorphic to the natural numbers. But the questions we ask, so if we ask if 2 plus 3 equals 5, then this doesn't necessarily mean that 2 is understood in the same way between the teacher and the student. So 2 might actually refer to something else. But still, this is the only kind of question we can ask in order to understand each other. And so, of course, the standard model is one that is isomorphic to n. And I mean, this is we will ask in our games atomic formulas, which are very basic questions. I mean, as the one I just said. So, in order to understand if someone with whom we're talking understand arithmetic as I do, I try to ask basic questions like, is 7 plus 5 equals 12 for you or not? And based on that, I mean, based on, of course, truthful responses by the students, we'll try to understand the model. And so we ask specific questions, and we get as an answer how these questions are interpreted in the model of the students, and on the basis of this, the teacher can actually come up with some conjecture on whether the model is standard or not. So in general, that's the structure of the game. So at step n of the game, we have I'm the teacher, and I ask a student. So depending on what happened before, I ask a specific question about the atomic diagram of arithmetic, and I receive a truthful answer determined by what the student has in mind as a model of arithmetic. And on the base of this, I can output a conjecture on whether the model is standard or not. And the strategy is just, a function from previous steps of the game that outputs, a conjecture on whether it's standard or not, and then I'll ask a new question based on what I heard before. And the new question is about, the atomic diagram. So I'll ask something specific about the atomic diagram. And the winning strategy is just a strategy that determines the step of the game that converges, meaning that if it converges to standard, this is exactly because the model is standard. So if I converge on my strategy to standardness, is because I managed to get the right model out of our discussion. But of course, this is a limit process, so I might not know whether the process will converge or not. I mean, there's no closed cone. At some point, I might just continue asking, but it's just about what happens in the limit. This is, of course, an idealization, but of course, because we have a finite amount of time. But in the end, I mean, this is something like, in principle, it is possible to agree on what we have. But then, I mean, of course, this will not answer completely the skeptical objection about whether we can understand each other, because that also has a finite component that is not avoidable, and there's no way out. I mean, and we'll see also, because this is an important aspect. I mean, given a finite piece of information, there is no way of determining whether the model is standard or not. It's only at the limit that we might do it. So, and then there is an important difference here, because there is something like in principle learnability and effective learnability. That is a distinction that will be relevant in confronting the second and the third game. So in principle learnability, something like, in principle, the game, I have a winning strategy that in principle can tell me if I can learn the model. But effective learnability means that the way I can understand is actually computable, meaning that there is an effective way of knowing if, in the limit, I won the game or not. And so this is an important distinction, exactly because, again, the basic idea is that we want to understand each other, and we want this to be effective in really sharing ideas about the standardness of the model of the arithmetic. So again, as I said, I mean, even if we work with in principle learnability, which is the weaker notion here, it doesn't mean that we have a finite step where we already know whether the series of conjecture converge. So I might not just know, and that's it. But in principle, I can learn whether the model is standard or not. But we actually want something more, because it's really about communication of the model, which I mean, also given all the discussion we had this week, seems to be a very important thing to us, because besides having the ability in principle to pin down, I mean, to actually separate the standard from the non-standard model, it's important that this happens in an effective way. Okay, so that's the definition of game one. Before the play begins, the student chooses an arbitrary M. So it's a model of the true arithmetic. It's a model that is in bijection with omega. So its domain is omega. Then the teacher has atomic access to its labeled presentation, meaning that I can ask specific questions about numbers and about operations, and then the student interpret them in his or her model, and then give me an answer about whether this holds or not. And the game is that I must identify in the limit whether the model is isomorphic to the standard one or not. And the difficulty of the game is the distinction between standard and non-standard lies in the global organization of the presentation, not in parameter-free first-order truth. So it's really about, I mean, I cannot really ask the right question. It's really a process that that in the end gives me the knowledge about standardness or non-standardness. And of course, I mean, I can revise my conjecture on whether it's standard or not indefinitely. Okay, so this is an important little lemma that is essential exactly for this finite limitation that says that, so if you fix a non-standard model, a finite partial atomic diagram is realized by a standard presentation if and only if it is realized by a copy of M. Meaning that if I have a finite amount of information, that is compatible with a non-standard and a standard model. So given a meaning that at a finite step of the game, what I see and my conjecture is compatible with either this being the standard model or not being the standard model. And the proof is actually simple exactly, and the idea is because they share the same truth arithmetic. So as long as I have finitely many information, I can just put all this information together and make an existential sentence that it will be also true in the other model. And then just by renaming labels, I can make it compatible with the other model. So again, this is an important thing because it says that at the finite step of the game, there's no way of me understanding it. So it's really in the limit that I can converge to standard or non-standardness. But again, this is still possible to understand what happens in the limit. Just to add a piece of notation, a node is admissible if just it occurs in some initial history for some M, meaning that it happened in some stage of the game. And the important lemma here is that that gives me actually the non-existence of a winning strategy for the game one is that if S were winning in the game one, then every admissible S, so if I'm at a fixed step of the game in game one, and this step has an admissible extension where the conjecture I had at S will be flipped. So I will change my conjecture as step tau. Meaning that even if S were winning. So this means that whatever is my strategy, if I don't have any constraint on my game and on my presentation, model presentation of true arithmetic, there is always a way to extend the game in a way that the conjecture changes. And this means, let me just check, yes, and this means that that there's no way of having a winning strategy that converges. And exactly because this is exactly what happens in the proof of the first theorem about the first game. So the teacher has no winning strategy. Exactly because whatever is my winning strategy, I can always, at some point, extend it in a way to flip my conjecture about standard or non-standard to the other one. And then again, at some point, I can do it again, and I flip back. And then it goes on forever, and I always flip from standard to non-standard. Which means that in the end, I will not converge in neither standard nor non-standard. And that's the idea. So I mean, and this is exactly the proof. I mean, if the current conjecture is standard, then I continue inside the non-standard copy until the person then conjecture that it might actually be a non-standard copy, and then I flip to the standard copy and I continue. I mean, I'm playing the models against the strategies, and this allows me to flip the conjecture. And then, I mean, there is a compactness Hankin construction at the end, just to put all these things together and have a presentation of the model for which the strategy will always have to flip from standard to non-standard and will not converge. Again, let me see. Maybe this is not really necessary. Yes, this is not really. So I mean, this what happens in the first game is that given this setup of the game with no constraints on the model of arithmetic, and given that the information at every step are finite, there's no way of having a strategy that will converge about standard or non-standard. So so let's go to game 2. The game 2, the interaction is exactly the same between questions and answers. But at the very beginning, the student has this constraint. If he or she chooses a standard model, then sum in that model must be computable. Okay, so so what happens is that the student has two choices at the very beginning: choose a standard presentation with plus computable, or anything else that is non-standard. Okay. So, and in fact, this is exactly the game suggested by Tenenbaum's theorem, exactly because, I mean, the non-standard models of arithmetic do not support a computable operation. And so if the model is standard, we want besides being standard, that the sum is computable. So we are not allowing standard models without computable operations. That's the only part that we are not allowing in this game. So what happens here is that this is kind of the strategy of the teacher in order to understand. So first, before starting the strategy, we fix an enumeration of all total computable binary functions, okay, which are possible functions that represent sum. And then we have two modes of playing in the game along this strategy. One is the standard mode, and the other one is non-standard mode. Okay, if I am in the standard mode, I will test one specific index of my enumeration of the functions that corresponds to the function fe, and I'll try to see whether the sum displayed by the student is actually that function. Okay, so I'm trying to ask question about, so if that is your function, if I assume if this is the function that represents the sum, how would you respond if I ask you this number plus this number equals that other number? And I try to see if this works. Okay. If I realize that this is not the one I was interested in, so there's, this is not the function that represents the sum of the student, then I change to the non-standard mode. What I do in the non-standard mode? Well, I try on the same index to search whether this is a non-standard number. Okay, so step by step, I'm kind of dovetailing on all possible functions that represent the sum and all possible numbers that might be non-standard. And if I find something wrong on one side, so then I switch to the other one. Okay, because there is a, I mean, you can know in a finite many steps if the function is not the one represented, if the sum is not represented by the function fe. And I also know in a finite number of steps if e is not a non-standard number, because I try to see whether in finite many steps I get back to 0. So, and this is a strategy of trying for an unbounded search on all possible natural numbers and on all possible computable binary function that represent the sum. So the first searches try to understand whether this is the real addition, and the other one trying to find some non-standard. And if these fails, I change to the other mode. And so what happens is that this is a winning strategy for game 2. So exactly because if the standard presentation is the one chosen by the student, at some point I will never get out of asking a question about the right sum. So if I got that that is the right function, I will stay then indefinitely, and that will converge to standard, because I will never find a mistake that separates the function, the sum that the student has in mind, from the function I'm considering that can be one of the computable functions. On the other hand, if the model is the non-standard one, it means that at some point one of the indexes for which I'm conjecturing that it's a non-standard number will never find the predecessor, will never get to 0 asking about the predecessor, and predecessors. And this means that I will stabilize on the non-standard conjecture. Okay? So this means that either I converge on standard, but of course, as you can see from the strategy, I will never know at some finite step whether I will stay indefinitely on standard or non-standard. But in the limit, I will know. So in principle, this is, I mean, and given the church Turing thesis, my hand wave of describing how the strategy works is exactly a way of describing how it's really a description of the strategy. But as you can remember here, I fixed at the very beginning an enumeration of all total computable binary function. And this is a problem. Exactly because, I mean, in order to do that, I cannot do it in a computable way, because that's the ultimate problem. So, so the strategy actually relies on the ability of having a complete enumeration of all computable functions, because I'm trying to test them one by one, and that's a strategy. So, of course, this is not a proof that there is no I mean, in discussing with Luca, we actually now proved that not only this strategy is not computable, but there is no computable winning strategy for game 2. But sorry, there's no yes, there is no computable winning strategy for game 2. I mean, we have one which is non-computable, but none of the others are computable. Okay. And again, why this is a problem? Because I mean, if in order to understand each other that we are talking about the same natural numbers, we need to solve the halting problem. That's an issue, because we don't really understand each other, because that's an oracle that told us exactly how to, if we are actually talking about the same thing. And then we get to game 3, which is, I mean, a further restriction on the presentation, in the sense that, again, we impose the student to choose either a non-standard model of arithmetic, presentation of a standard model of arithmetic, or if it is standard, then the operation must be primitive recursive. Okay, so no model which is standard with non-recursive operation is allowed, and no model which is standard with just recursive and not primitive recursive functions are allowed. So we're kind of restricting the choice of the student, which is again another idealization in how things are. But I mean, it's not such a wild generalization, because in the end, this is what we learn at school. That we learn sum and the basic operation in primitive recursive terms. And again, here the main point is that there is a computable function that enumerate all primitive recursive functions, and that's the really important aspect. Exactly because what happens here is that in game 3, the teacher has a computable winning strategy, because it's exactly the same strategy we had before, like staying standard, trying to test all the available functions, or staying non-standard, trying to get if a number is a non-standard number or not. But now everything depends on the on an effective list of all primitive recursive functions, because exactly as in game 2, that the strategy depended on fixing an enumeration of all recursive function, and that was the issue about effectiveness. But now we have that we can list all primitive recursive function in an effective way, and that's give me not only a winning strategy but an effective winning strategy, because at each point we know how to calculate what is the next function we want to test in our strategy. Okay, so yes, this is not really needed. So in general, I mean, this is just a more general winning strategy for any game which allows an effective enumeration of all functions that we're trying to test. So it works in the case of primitive recursive functions, but I mean, of course it can work even with other classes of functions. And so again, this is just to review the general results. So we have again 3 games. The first one where is no restriction on the presentation. The second where we add that the natural, the standard model should has computable operations. And the third one when the computable operations are actually primitive recursive. And what is the consequence of this? So in the first epistemic consequence, because the idea is that we really want to understand each other in sharing our knowledge of arithmetic and trying to understand if really there is an agreement, the one that Rodrigo was talking about. So if we have no restriction at all on any kind of models that we might actually think of, so there is no way of understanding and learning that we're sharing the same model, meaning the true standard model. So if we assume, which is again, this is the game 2 is Tenenbaum's game in some sense. If we assume that the operations are computable, in principle, there is a way of understanding each other, but there's no effective way of doing it. So we can understand each other even. So Tenenbaum results seems to show that in principle we can understand each other, but not in an effective way, and that's an important part. And the third game is actually what probably happens in practice. I mean, we have an effective way of understanding each other, even though if it's just in the limit, but there is a way of understanding each other, but we have to assume that if the model is standard, then the operations are primitive recursive. So yes, again, this is in some sense what I've just said. So Tenenbaum already gives a separation between standard and non-standard, but it doesn't really give information about learnability of the model. So it doesn't really give a way of having a shared content in our understanding of arithmetic. And exactly because, I mean, the presentation actually of the model is essential. And if we have that the presentation is not primitive recursive, then even if in principle we could understand that we're talking about the same thing, but in practice this doesn't happen. And so, I mean, that's also a more general point about the role of computability in the problem of fixing the model of arithmetic, because it's not just that in principle we can do it, as Tannenbaum shows us, but in order to do it for real, we need to impose something more. And that's actually interesting, because it's first of all, it provides, but that already Tannenbaum was doing this, a very important role for computability theory in this discussion. And that's actually why I decided to present this talk, because it was adding some layer of difficulty in this discussion. When things become effective, I mean, you need some more hypothesis on the way we actually have this in Wittgenstein terms form of life that we share. And also, I mean, what is interesting and new in this, that it's not only computability, but primitive recursiveness seems to have an important role in this, which is not something that normally is stressed. Yeah. So, but also, I mean, it's important to separate what this consideration provide us and what they do not, because I mean, as you've seen from the setup of the games, we are not really able, using this game, to single out the real model of arithmetic, exactly because the more and the more we have constraints in the game, the more models we're actually leaving outside already from, because it's not a complete we're not separating the space of models into categories, but we're just imposing condition. There are reasonable condition on communication. And again, it doesn't really help fixing the terms, also because, first of all, it happens in the limit, but also because it's really something that depends on the presentation of the model, and not just on hypotheses and general hypotheses about our understanding of arithmetic. And again, as I was saying before, I mean, it shows the importance of a primitive recursive in this context. Yeah, no, that was an old version of the slides. So this, we already know that the G2 has no computable winning strategies. And let me, yeah. So yes, just to conclude, three important lessons that we can learn from this is that first of all, determinacy is not transparency, in the sense that if you notice in the game, the student has a very well fixed model of arithmetic in mind, but the question is whether we can access that model. It's not whether it's indeterminate which the model is, because the model is fixed, but it's really about how we can get access of, I mean, another mind in some sense, or other form of representation, without only having finite amount of information. And also the presentation constraints have epistemic force, in the sense that the way the model is presented, the condition we impose in the presentation of the model provide access to the model of the student. And this is exactly the point of computability. So if the presentation of the model really imposes condition on how the arithmetic is presented, and of course this is completely opposite to any Platonistic way of understanding model theory, because I mean it's really about how things are presented, the choice of the language, the choice of the properties of the interpretation of the functions. And again, the real moral of the talk is that effective survivability yields effective learning, meaning that it's really about primitive recursiveness that allows you to access in an effective way the model of the, I mean, again, in the limit, model of the limit, the model of the student. And that's it. Thank you very much.
Thank you, Giorgio. Questions?
Thank you, Giorgio. This is a very nice result, and you put very well the problem that the fact that we may have an agreement, if we have one, does not solve the problem of how can someone enter into that agreement,
yeah,
or recognize the agreement.
Yeah.
And the agreement that I have proposed as somewhat irreducible is on iteration or succession, as Alfredo's formulated it. And it is very interesting that in your result you require that form of limit idealization to recognize
the dots that you were writing the other days. Yeah,
I think that the only way out of this kind of idealization that we have, and this, of course, the problem of recognition, leads us to cognitive science, is to consider our sensorial dimension, not only the cognitive dimension, right? Because in the games you have proposed, they are cognitive. You are given formulas, atomic formulas, and asking questions and receiving answers. And I think that the basic agreements that we learned, the most basic, I learned before that stage. Right? They are learned by children through the development of vision, the audition, I don't know, the sensorial, which are not also innate, but the children is not born seeing with. Is not born seeing, but it develops through some kind of, I suppose, internal self-correcting mechanism, right? It receives the external image, and then something tells that it is not focused, and so it feedbacks to the optic nerve, and then it adjusts, and then it receives another image. It is not focused, feedbacks. Feedback. I think that this kind of feedback that is also in machine learning now is the basic mechanism of iteration that we somehow have in our sensorial apparatus, and also in our cognitive apparatus in general. And yeah, I think that is the last stage. Right? If someone is born without some important part of the sensorial dimension, it may not never achieve
Yeah.
The agreement, the kind of agreement that we had to do language and also mathematics. Therefore.
Yeah. No, I agree. I mean, it's this idea of numbers being God-given, like Kronecker was saying. I mean, it's a product of that time, which is not ours. I mean, we have a much better understanding of how the things work, and I agree with you. I mean, there's an idealization here that it's not avoidable, and but in the end, it doesn't explain really why we understand each other in such a good way. I mean, so I mean, but yes, these results actually points towards, in some sense, a continuity between, I mean, our theorization in first order logic, or I mean, in formal setting, and going down through some elements of computability theory that really it's about the way we use this formalization. But as you were saying, it also continuously goes down to some notion of cognitive science that explains where all these things come from. And because I mean, of course, going back, I mean, that's a general criticism about Tannenbaum and all these approaches on computability that try to fix the interpretation of arithmetic, that in the end also computability theory needs arithmetic to be developed. But I mean, as we were saying also these days, I mean, even I mean, to develop language, I mean, any kind of formal language, we need some form of arithmetic. So I mean, of course, I mean, it's really postponing where we explain where all this notion come from, and but given the this hybrid aspect of computability theory that is between some formal aspect and some real human way in which these things are understood. I mean, this is exactly a way to connect the formal aspect and the cognitive. So I mean, I agree. Then that's an interesting question that is not for a logician. I mean, that's there are cognitive scientists that know much more than us how these things work. But I mean, it's just nice to see how these things actually really reappear also in I mean, provably in our formalization of what it means to learn the model of arithmetic. Yeah, thanks.
Yeah, there we go. I'm a little unsure about exactly what's going on. The questions involve multiplication.
Involves, sorry?
Involve multiplication.
Multiplication. It's they're mainly yes. Also multiplication.
That's I mean, because you can't.
Yes. Sum and multiplication, and we assume both to be computable, or
that's
yes.
what you have to have. Right?
Yes.
Okay.
Yeah, no, exactly. I mean, yeah, maybe it wasn't very clear in the slides, but yes. I mean, the language is the.
It was the fact that you were only using computable addition.
Yes, no. I mean, it's yeah.
That's probably okay if you think the multiplication is.
Yes, exactly, because it's already in the language. We have a successor, sum, and multiplication. Yeah.
More questions, comments? No. So let's thank Giorgio again.
Thank you very much. And yeah, and again, thank for all the organizers and all the speakers. It was a very nice and useful week. So thank you very much to all of you.